Welcome, gentle listener, to Sleepy Facts. This is a quiet space where we let the world soften, and knowledge arrives like a slow, gentle tide. There is nothing to hold on to here, nothing to solve, only the soft rhythm of a story waiting to unfold. Let your shoulders fall your breath, find its own pace, and allow your mind to drift. Tonight, we begin a journey into a world that exists just beneath our own. A world not of solid things, but of shimmering possibilities. A place where reality seems to wait for us to look, and where the universe whispers its secrets, not in answers, but in questions. There is no need to understand everything at once. There is only the need to listen, to float, and to wonder. So find your comfort in a quiet room or on a sleepy train ride, and let us begin to drift into a world where even the firmest ground begins to feel like a dream, a soft and gentle dream of what could be. In a time not so long ago, the world we knew felt solid, predictable. It was a world of certainty, a well-swept room where the laws of physics were tidy and complete. If you dropped a teacup, it fell. If you flipped a coin, it landed. If you closed your eyes, the moon did not vanish. It was a golden age of knowing a time when it seemed all the great questions had been answered, and only a few odd bits of dust remained in the corners, waiting to be swept away. One of those dusty corners held a very simple idea. A question that should have been easy to answer. What happens when you heat something up? Imagine a piece of metal cool and dark in your hand. As you warm it, a soft glow begins to bloom from within. First, a deep, gentle red, then a warm and steady orange, and finally, a brilliant, shimmering white. This glow, this quiet release of light, is called black body radiation. It comes from the way all things share their warmth with the world, breathing out electromagnetic waves. It was something easy to see, something that felt ancient and natural, and it should have been simple to explain. And yet, it was not. The old rules, the ones that worked so beautifully for planets and pendulums, refused to cooperate. When scientists tried to describe this gentle glow with their trusted equations, the math began to unravel. The formulas predicted something impossible, a story that made no sense. They suggested that as an object grew hotter, it should release more and more energy at shorter and shorter wavelengths, spiraling into an infinite, impossible brightness in the ultraviolet range. A scenario so strange, so contrary to the quiet glow of a warm piece of metal, it was nicknamed the ultraviolet catastrophe. No matter how the numbers were arranged, no matter how the old laws were coaxed and adjusted, the math continued to spiral into this gentle madness. Reality, it seemed, was not following the story it was supposed to. Something was missing from the tale. And so, a quiet man entered the dream. His name was Max Planck, a German physicist known for his careful, methodical thinking. He was not a rebel. He was not looking to overturn the world. He believed in the solid classical view of the universe, but he was also a man who listened to the numbers. And when he faced this problem of the impossible glow, he did something quietly revolutionary. To fix the math to calm the spiraling infinities, he introduced a small, strange thought. What if energy was not a smooth, continuous river? What if it could not be given or received in just any amount? What if instead it arrived in tiny, indivisible packets, like quiet footfalls in the dark, like coins that you could not split in half? He called these packets quanta, the smallest possible units of energy. This was a profound shift from the world of smooth-flowing forces. In this new picture, energy would arrive in steps, in tiny discrete jumps that depended on the frequency of the light. He even found a number, a constant of nature, to describe the size of these energy packets. It was a number unimaginably small, a whisper of a value, but it was mathematically perfect. When he placed this idea into his equations, something miraculous happened. The infinite energy, the ultraviolet catastrophe, simply vanished. The math settled. The numbers breathed a sigh of relief and fell into perfect harmony with the real world. Max Planck had solved the puzzle. And yet, he didn't quite believe it. He saw his own solution as a mathematical trick, a clever way to make the numbers behave, but not a true description of how the universe actually worked. To him, these little packets of energy, these quanta, were a temporary patch, a placeholder, until a better, more sensible explanation could be found. He could not have known in that quiet moment of discovery that his trick was not a patch at all. It was the cornerstone of a whole new reality. His idea, the thought that energy arrives in discrete steps, laid the very first stone on a path that would lead to quantum theory. A theory that would soon unravel so much of what the solid, predictable world had taken for granted. Looking back, it is easy to see this as the moment everything changed. But at the time, it felt more like a strange and curious footnote than a revolution. There were no grand pronouncements, no sudden declarations, just a small constant number, a new way of thinking about energy and a gentle fix for a problem that refused to go away. Planck had not set out to challenge the foundations of physics. He just wanted the math to make sense. And yet, by introducing the idea of quanta, he had lit the first match in what would become a slow, quiet fire, one that would eventually reshape our understanding of light, of matter, and of the very nature of what is real. From that humble beginning, tucked into a paper published in the year 1900, the well-swept room of physics would never feel quite finished again. The dust, it turned out, was not dust at all. It was the beginning of a new world shimmering just out of view. And so the quiet fire began to spread. In the early years of the new century, light was thought to be understood. It was an elegant wave, a ripple in the electromagnetic field that bent and bounced and spread just as a proper wave should. After Max Planck's strange idea of energy packets, most believed things would settle back into a slightly adjusted but still familiar rhythm. But then came another riddle, a puzzle involving a piece of metal, a beam of light, and a surprising refusal to cooperate. It was called the photoelectric effect, and it seemed simple enough. When you shine a light onto a metal surface, tiny particles called electrons can be knocked free. The idea made sense. Light carries energy, and that energy could surely nudge an electron out of its metallic home. According to the old wave theory, a brighter light, a more intense wave, should carry more energy, and therefore it should shake the electrons loose with greater force. A brighter wave should mean more powerful electrons. That was the expectation. But that is not what happened. In quiet, careful experiments, a different story emerged. Shining a brighter light did not necessarily give the electrons more energy. What mattered was not the brightness, but the color, the frequency of the light. If the light was below a certain frequency, a deep red, for instance, then even a blindingly bright beam did nothing at all. No electrons were nudged free. They remained still unmoved. But if the light was above that frequency, a soft blue or violet, then even the dimmest, faintest beam could knock electrons free with ease. The line was sharp, absolute, and it made no sense in a world where light was only a wave. This small inconsistency bloomed into a quiet, profound mystery. And then another mind entered the dream: Albert Einstein. In a year often called his miracle year, he offered a bold and beautiful explanation. What if light was not just a wave? What if, under certain circumstances, it also behaved like a particle, a tiny, discrete bundle of energy? Building on Planck's idea, Einstein suggested that light itself was made of these energy packets, which he called quanta of light, later to be known as photons. Each photon carried a specific amount of energy determined only by its frequency. If a single photon had enough energy, it could knock a single electron loose. If it didn't, then no amount of photons, no matter how bright the beam, could do the job. It was like trying to open a locked door with a handful of keys, none of which fit. No matter how many keys you tried, the door would not open. But a single key of the right shape would turn the lock with ease. Einstein was not just using these energy packets as a mathematical trick as Planck had. He was suggesting that this was what light was, not just a wave, but also a stream of particles. It was a revolutionary claim, and many physicists clung to the familiar comfort of the wave model. After all, light clearly behaved like a wave. It bent around corners. It created interference patterns. How could it be made of particles? Einstein did not deny the wave nature of light. Instead, he proposed something even stranger. Light, he said, was both. It was a wave and it was a particle. It could act like one or the other depending on how you chose to observe it. This idea, this wave-particle duality, is one of the softest and strangest truths in all of science. Not because it is complex, but because it challenges the very way we sort the world into neat boxes. In our everyday world, things are either one thing or another. A stone is a particle. A ripple in a pond is a wave. But the quantum world does not ask for our permission to make sense. Imagine a beam of sunlight filtering through a window. It spreads and drifts like a wave, catching dust motes in its soft glow. But if you could look closer, much closer, you would find tiny individual packets of energy, each with its own color, its own frequency, gently colliding with the world, one photon at a time. The dream deepens, and the solid ground gives way. Einstein's explanation of the photoelectric effect was beautiful. It not only solved the mystery of the metal and the light, but it did so by revealing a deeper, stranger truth about the universe. For this discovery, he was awarded the Nobel Prize. And yet, even he found the quantum world uncomfortable. God does not play dice with the universe, he would later say, a quiet protest against the shimmering uncertainty his own work had helped reveal. But whether by design or by dice, the rules of the world were changing. And at the heart of those changes was the strange truth that light, the very thing that illuminates our world, refused to fit into any tidy box. It arrived in packets. It danced as a wave. It collided like a particle. It shimmered between states of being, revealing just enough to keep us wondering, and just enough to keep us unsure. What began as a simple puzzle with light and metal had shaken the very foundations of what we thought was solid. Because if light could behave this way, both continuous and discrete, both spread out and point-like, What else might be lurking in the quiet corners of the universe, waiting to break the rules? Imagine for a moment a simple table in a dark room. At one end, a small source of light like a single candle flame. And in the middle, a piece of cardboard with two tiny parallel slits cut into it. Behind the cardboard, a screen waits to catch whatever passes through. Two holes and a bit of light. It sounds like the beginning of a child's game. And yet, in this humble arrangement, we find one of the most profound and mind-bending experiments in all of science. It has been called the most dramatic story in physics, starring only a beam of light and a piece of cardboard. This is the double-slit experiment. Let's begin with what we would expect to see in the familiar world of our senses. In that world, waves and particles behave very differently. A wave, like a ripple in a quiet pond, spreads out. When it meets a barrier with two openings, the wave passes through both, and the two new waves interfere with each other on the other side. Where their peaks meet, the wave grows stronger. Where a peak meets a trough, they cancel each other out, creating a place of stillness. This creates a distinct pattern of bright and dark bands, a signature of interference. It is a well-understood and gentle dance. Now imagine particles like tiny grains of sand tossed gently at the same barrier. Some would pass through the left slit, some through the right. They would not interfere or overlap. On the screen behind you would simply find two small clusters of sand, marking the spots directly behind each slit. A straightforward, predictable result. So what happens when we do this with light? When scientists first performed this experiment, shining a beam of light through the two slits, it behaved just as a proper wave should. It spread out, and on the screen, a beautiful interference pattern appeared, a series of soft, glowing bands, a perfect testament to the wave nature of light. So far, so good. The world was behaving as expected. But then the experiment took a strange and wondrous turn. Using very sensitive equipment, the light source was turned down, dimmed, until it was firing just one particle of light, one photon at a time. A single lonely traveler making its way toward the slits. Now you would expect these individual photons to act like particles, like those tiny grains of sand. Each one should pass through either the left slit or the right. And if you waited long enough collecting the landing spots of thousands of these single photons, you should see two simple bright clusters on the screen. But that is not what happened. Even when sent one by one with long, quiet moments between each arrival, the photons slowly, patiently built up the very same interference pattern as before. A pattern that could only be created if waves were passing through both slits at once and interfering with themselves. But how could a single photon interfere with itself? Did it somehow split in two, passing through both slits at the same time? Was it a wave and a particle in the same quiet moment? The pattern on the screen was undeniable. It suggested that each lone photon in its journey had not chosen a path. It had, in some ghostly way, explored every possible path. It had passed through the left slit, and it had passed through the right slit, and it had interfered with its own ghost, its own potential, before finally arriving at the screen as a single, definite point. If that wasn't strange enough to quiet a room, what happened next was even stranger. The physicists decided to peek. They decided to watch. They placed tiny detectors at each slit to observe which path each photon actually took. Surely, they thought, we can settle this. Did it go left or did it go right? But the moment they looked, the moment the detectors were turned on, the interference pattern vanished completely. As soon as the photons were observed, they stopped behaving like ghostly waves. They acted like ordinary, well-behaved particles again. They passed through one slit or the other, and on the screen they created two simple bright clusters. No more interference, no more shimmering possibilities. It was as if the very act of observation had forced the photon to make a choice. Go left or go right. No more superposition, no more fuzzy in-between states. Reality had been caught in the act of being strange, and it immediately straightened up and acted normal. Turn the detectors off, and the interference pattern would softly return. Turn them on, and it would vanish again. The implications were staggering. It wasn't that the detectors were clumsy, physically disturbing the photons. The issue wasn't how they observed, but that they observed at all. It seemed that the mere potential for knowledge, the ability to know which path the photon took, was enough to collapse its wave-like behavior into a simple particle state. Reality, in a soft and subtle way, seemed to care whether or not it was being watched. This was no fluke. The double-slit experiment has been repeated countless times, with photons, with electrons, and even with large molecules made of hundreds of atoms. And the result is always the same. Left unobserved, these particles of matter and light act like waves, spreading out and interfering with themselves. Observed, they behave like classical particles falling neatly into line. If this sounds unsettling, you are not alone. This simple experiment sits at the very heart of quantum physics, and it resists every effort to be explained in familiar terms. It suggests that on the smallest scales, particles do not follow definite paths. They exist as a spread of possibilities, a shimmering cloud of potential outcomes. Only when a measurement is made does that cloud collapse into something definite, something real. What began as a simple test of light has become a profound mystery about the nature of reality itself. Is observation an active part of shaping the universe? Does information have power over existence? Is the world fundamentally uncertain until we ask it to reveal itself? The double-slit experiment does not give us clear answers, but it does give us one powerful, quiet insight. The universe, at its core, is not a clockwork machine. It is a strange and shimmering tapestry woven from possibility, and it responds in the most curious of ways to our gaze. With two slits, a source of light and a screen, we discovered that the universe winks at us when we are not looking, and stands perfectly still when we are. And so, the dream drifts deeper into this quiet mystery. In this shimmering, uncertain world, a new kind of language was needed. The old words, the old equations of motion and force could not describe a particle that was in many places, at once a reality that waited to be seen. The universe, it seemed, was whispering a new story, and physicists were learning how to listen. If there is a secret spell that runs through this entire quantum dream, a quiet heartbeat that pulses beneath the surface of it all, it is an equation. Now there is no need to think of math, no need to picture numbers or symbols on a dusty chalkboard. This is not that kind of story. Think of it instead as a mathematical whisper, a quiet, elegant line of thought that describes not how things are, but how they might be. Back in the 1920s, the old laws of motion were no longer enough. The universe needed a new grammar, a new way to speak of waves that acted like particles, and particles that behaved like ghosts. And in 1926, a physicist named Erwin Schrödinger offered just that. He proposed an equation that described not the path of a particle, but the gentle evolution of its possibilities over time. At its heart is a concept called the wave function. If that sounds abstract, let it be soft. Imagine the wave function as a cloud of might be, a hazy, rippling map of where a particle is likely to be found. In the old solid world, if you wanted to describe a particle moving through space, you would draw a neat, clean line, an arrow showing its exact position and its exact speed. But Schrödinger's world does not draw lines. Instead, it gives us this soft, shimmering cloud, a wave of probability that says the particle is likely to be here. But it could also be there, and perhaps just a little bit over there too. This is where the quiet magic happens. Schrödinger's equation is the rule that guides this cloud. It shows how the wave of possibilities shifts and flows through time. It describes how the likelihood of finding the particle in one place fades, while the chance of finding it somewhere else grows stronger. And when we finally look, when we ask the universe, "Where are you?" that is the moment the wave function collapses. The shimmering cloud of might be instantly vanishes, and we are left with a single definite answer, a single point of reality. Here it is, right there, but only after we have looked. This wave-based view of the world is profoundly different from the clockwork universe that came before. Instead of solid objects tracing predictable paths, we now see swirling fields of probability full of a gentle ambiguity until the act of observation pins them down. Let's soften this idea even more. Imagine you are standing blindfolded in a quiet room. Somewhere in that room is a very still, very silent cat. You cannot see it or hear it, but you have a handful of soft woolen balls. You can toss them gently into the room and listen for the sound they make when they land. Over time, you begin to build a mental map, a map of possibilities. The balls that land with a soft thud on the rug tell you something. The ones that make a gentle click against a wooden chair leg tell you something else. You are not building a picture of where the cat is, but a map of where it might be. Areas with a higher chance, others with less. That map, that shimmering cloud of likelihood you are building in your mind, that is like the wave function. Now imagine you could write a rule, an equation that tells you how that map of possibilities changes over time. Perhaps the cat likes to move toward warm corners, or perhaps it avoids the draft from the window. That equation would be your guide to where the cat is likely to be next. That is what Schrödinger did. But instead of cats and woolen balls, he was thinking of electrons and atoms. His equation is smooth and continuous. It allows these waves of probability to ripple and shift with a quiet, natural grace, like water in a pond. It does not speak in absolutes. It does not say what will happen. It only whispers what could happen. And what is truly wondrous is how beautifully it works. This gentle, probabilistic equation has been used to describe the world with astonishing accuracy. It explains the structure of atoms, the way molecules bond together, the behavior of the tiny transistors that power our modern world. It even predicts strange and beautiful phenomena like quantum tunneling, where a particle can slip silently through a barrier it should not have the energy to cross. One of its most famous successes was in describing the hydrogen atom, the simplest atom in the universe. For a long time, no one could explain why the electron orbiting the nucleus didn't simply spiral inward and collapse. The old rules said it should. But Schrödinger's equation revealed a different story. The electron is not a tiny planet whizzing around a sun. Instead, it forms a standing wave, a stable, shimmering pattern of probability that surrounds the nucleus. You may have seen these patterns drawn in old textbooks as soft clouds or gentle symmetrical shapes. These are not just artistic ideas. They are real measurable maps of where the electron is most likely to be found. They are not orbits. They are zones of presence. And they exist only because the electron is not a simple particle. It is a ripple in a sea of probability. It is strange, certainly, but it is also beautifully consistent. Schrödinger's equation has stood the test of time, predicting the behavior of the very small with a precision that is almost miraculous. And yet, it remains hauntingly abstract. You cannot hold a wave function. You cannot see it. But it is there describing the ghostly potential of everything, from a particle of dust in a sunbeam to the atoms in your own hand. Even Schrödinger himself had mixed feelings about the world he had described. He gave us the mathematics of these quantum waves, but he disliked the idea that reality remained so undecided until it was observed. His famous thought experiment, the one involving a cat that is both alive and dead, was meant as a quiet critique of the very uncertainty his own work had unleashed. Still, it is hard not to feel a sense of wonder at what he built. In a world that so often demands clear, simple answers, yes or no, here or there, Schrödinger offered something gentler, a shimmer of maybe, a softly pulsing guide to what could be. His equation does not shout or command. It suggests, it flows, and in doing so, it reveals a version of the universe that is quieter, subtler, and far more mysterious than we ever imagined. A world where, on the smallest scales, motion is not always motion. Position is not always position. Uncertainty is a luxury that nature does not always afford. But even this shimmering, uncertain world has its own rules, its own soft boundaries. The silence widens, and we follow. In the world of our senses, the world of apples and rain and quiet footsteps, we can know where something is and how it is moving all at the same time. A train pulling into a station has a location and a speed. A leaf drifting on the wind follows a path we can trace. There is no mystery here, no contradiction. But the quantum world does not play by these familiar rules. In the 1920s, another physicist named Werner Heisenberg introduced a principle so central to this new reality, so strange and so soft that it stills the mind. It is called the uncertainty principle, and it tells us that at the most fundamental level of the universe, there are gentle, unbreakable limits to what we can know. It whispers this simple truth: the more precisely we know a particle's position, the less precisely we can know its momentum, its motion. And the more we know of its motion, the less we know of its place. It is a cosmic trade-off, a perfect, delicate balance. In our everyday thoughts, this sounds almost impossible. How could knowing where something is make you unsure of how it is moving? But at the quantum scale, reality does not allow for that kind of perfect clarity. And this is not because our measuring tools are clumsy or our eyes are not sharp enough. The uncertainty is not in our instruments. It is woven into the very fabric of existence itself. Imagine you are trying to find an electron to know both where it is and where it is going. To see it, you must shine a light on it. But light is made of photons, and photons carry a gentle push, a tiny transfer of energy. The moment a photon touches the electron to reveal its position, it changes the electron's motion. It is a little like trying to find a soap bubble in a dark room by softly tossing grains of sand at it. You will eventually find it, but in the very act of finding, you will have altered its delicate state. But Heisenberg's point was even deeper than this. The uncertainty is not just a side effect of our looking. It is a fundamental feature of the wave nature of all things. Think of a single, long wave rolling across the ocean. Its motion, its momentum is clear and steady. But where exactly is the wave? It stretches out a long, gentle swell. Its position is soft, undefined. Now imagine a short, choppy wave, a sharp peak in the water. Its position is clear right there, but its motion is a jumble, a mixture of many different speeds. A particle like an electron is also a wave of possibility. If that wave is long and smooth, its momentum is knowable, but its location is a gentle blur. If you squeeze that wave to pinpoint the particle's position, the wave becomes choppy and its momentum becomes a mystery. There is no way around this cosmic balance. The more you have of one kind of knowledge, the less you are allowed of the other. The product of the two uncertainties can never be zero. It will always be more than a tiny fundamental number, a constant of nature that sets the scale for this graceful fuzziness. In our large and heavy world, this effect is so small it is invisible. You can measure the position and the speed of a falling raindrop with incredible precision and never feel the whisper of this quantum limit. But for the tiny, weightless dancers of the subatomic world, this uncertainty shapes their entire existence. If you try to trap a particle in a very small space to pin down its position, it begins to resist. Its momentum becomes wildly uncertain, and it starts to zip and shimmer unpredictably. It is as if nature does not like to be told exactly where things must be. This is not a flaw in the machinery of the universe. It is a softness that cannot be wiped away, a blur that is part of the picture. One way to feel this is to imagine trying to hold mist in your hands. The tighter you squeeze, the less of it you can hold. Open your hands just a little, and more of it can linger. That is the gentle balance between knowing too much about one thing and being forced to let go of another. In many ways, the uncertainty principle is a philosophical whisper, a soft warning label on the quantum world. It tells us that knowledge has boundaries, not because of our own limitations, but because of how reality itself is built. We are not dealing with tiny, solid billiard balls rolling through space. We are dealing with possibilities, with probabilities, with waves that refuse to be pinned down too tightly. This principle also explains why the atoms that make up our world are stable, why the electrons with their negative charge do not simply fall into the positively charged nucleus. The uncertainty principle will not allow it. If an electron were to fall into the nucleus and stay there, its position would be known almost perfectly, and that would mean its momentum would become almost infinitely uncertain. That would require an infinite amount of energy. And so, nature gently says no. Electrons hover in their soft clouds of probability, not because they are choosing to, but because the quantum rules will not allow them to be still. The uncertainty principle creates a kind of built-in resistance, a gentle push back against absolute confinement. And in this strange and beautiful limit, there is something comforting. Uncertainty in this sense is not chaos. It is a structured ambiguity, a kind of graceful, knowing softness. It gives the universe its texture. It allows particles to tunnel through barriers they should not be able to cross. It allows chemistry to happen. Without it, reality might be too rigid, too perfect to support the messy, wondrous thing we call life. So much of our world is built on finding certainty, on predicting and measuring and knowing. But this quiet principle invites us to do something different. It invites us to make peace with not knowing, to sit quietly with the blur, and to appreciate the softness of what lies just beneath the surface of the solid world. It is a reminder that the deepest truths are not always sharp-edged, but cloudy and rippling and unresolved. And in this world of gentle blur, where nothing is ever perfectly pinned down, particles are allowed to do something even stranger. They are allowed to be in more than one place, in more than one state, all at the same time. In our everyday experience, the world is made of choices that have been made. A light switch is either on or it is off. A coin, when it lands, shows either heads or tails. A door is open or it is closed. Things tend to be in one state or another. But in the quiet, shimmering world of the quantum, this tidy division of reality breaks down. Objects on the smallest of scales do not always pick a side. They can linger in a strange and beautiful in-between, a soft blend of all their possible outcomes at once. This is the gentle realm of quantum superposition. To picture this, imagine holding a single shining coin. In the classical world, when you flip it, it travels through the air spinning on a clear path. You may not know which side will land face up, but it is always one or the other, even while it is hidden from your view. Quantum systems do not work this way. If you could flip a quantum coin, it would not secretly be heads or tails as it spun. Instead, it would enter a state of superposition, a weighted combination of both heads and tails at the very same time. It is not undecided. It is not switching quickly between the two. It is in a way that our senses can barely grasp genuinely and physically, in a state that is both until you look. And when you do look, when you open your hand to see the superposition collapses, the quantum coin chooses a face, and your measurement becomes a single solid reality. But a moment before you looked, it was not just unknown. It was both. This is a soft and difficult thought to hold. It is not just strange, it is deeply, profoundly weird. This idea first arose as a way to describe the behavior of particles, like electrons and photons. These tiny dancers, rather than following neat, predictable paths, exist as wave functions, those shimmering clouds of probability. Each possible state, a spin pointing up or a spin pointing down, a photon going left or a photon going right, is part of this cloud. And all of these possibilities coexist layered gently on top of one another until a measurement asks the system to choose one. You might picture it as a foggy landscape of outcomes. A particle does not walk a single path through this mist. It is more like it has spread itself out, smearing its own potential across every possible route it could take. When you interact with it, that soft fog of possibility suddenly snaps into a single definite location. A specific outcome, like a quiet flash of lightning illuminating one single hilltop in the mist. This strange concept led to one of the most famous thought experiments in all of physics. It is a story you may have heard before, a quiet and curious tale known as Schrödinger's cat. Imagine, he said, a sealed box, a Inside this box is a cat, and alongside the cat is a single radioactive atom, a detector, and a tiny vial of poison. The fate of the cat is linked to the fate of the atom. If the atom decays, something quantum mechanics tells us happens at a completely random moment. The detector will notice, and it will trigger a mechanism that breaks the vial. If the atom decays, the cat will not survive. If it does not decay, the cat will remain perfectly safe. But here is the quantum twist. Until the atom is observed, quantum theory tells us that it exists in a superposition of states. It is both decayed and not decayed at the same time. And if the atom is in a superposition, then the entire system linked to it must be as well. The detector, the poison, and yes, the cat. And so until someone opens the box to look, the cat is in a superposition of being both alive and not alive. This was never meant to be a real experiment. Schrödinger was gently highlighting the absurdity of applying these strange quantum rules to large familiar things like cats. He found it difficult to imagine that an animal with its warmth and its breath, and its clear preference for sunny spots, could exist in such a blurry, undefined state. And yet, the idea has stayed with us because it captures the very essence of quantum uncertainty in a single, unforgettable image. A cat that is both here and gone until the very moment we look inside. It is a powerful way to express what it means for a system to remain unmeasured. It is not about indecision, it is about possibility. Until observation collapses, the wave function the system holds within it, every potential outcome, all futures, all states at the same time. And yet, for all its strangeness, superposition is not a flaw in the theory. It is one of its most powerful and beautiful features. Much of our most advanced technology is now being built upon this very idea. Think of a quantum computer. In the computer or the phone you use every day, information is stored in bits. A bit can be a 0 or a 1, an off or an on. Every photo, every word, every song is a long and beautiful string of these simple binary choices. Quantum computers use something different. They use qubits. And a qubit, unlike a simple bit, can exist in a superposition of both 0 and 1 at the same time. This means a single qubit can hold more information than a classical bit. And when you link many qubits together, their power grows exponentially. They can explore a vast number of possibilities all at once, not by checking them one by one, but by holding them all in a shimmering computational cloud. But there is a reason we do not see this quantum weirdness in our everyday lives. Superposition is delicate. It is a fragile, whispered state. The slightest interaction with the outside world, a stray particle of light, a tiny vibration, even a single warm air molecule can cause the beautiful superposition to collapse. This process, this gentle loss of quantumness, is called decoherence. It is one of the greatest challenges in building quantum machines. It is like trying to balance a feather on the tip of a needle while a soft breeze is blowing through the room. The moment the system is disturbed, the quantum magic vanishes. That fragility is part of what makes these systems so wondrous. They offer us a glimpse into a world of immense possibility, but only under the quietest, most isolated conditions. They ask us to rethink what it means for something to simply be. And this leads us to a deeper, softer question. If a particle can truly exist in multiple states at once, is that a description of reality itself? Or is it just a reflection of what we are allowed to know? Quantum superposition invites us to loosen our grip on the solid logic of the everyday world. It tells us that opposites can coexist, that a system can be both this and that, here and there, yes and no, all at once. That reality, at its very core, is not a single solid thread, but a tapestry of possibilities overlapping and unresolved until the gentle act of observation pulls one single strand loose. It is strange. It can be uncomfortable, but it is also beautiful. Because in this strange rule of superposition, we find a universe that is not rigid, but flexible. Not mechanical, but poetic. A world that allows for contradiction and for uncertainty, not as flaws, but as features. And in that gentle allowance, new ways of being, of computing, and of dreaming become possible. And from this state of shimmering possibility, an even stranger connection emerges. One that links particles together, no matter how far apart they may be. Imagine you have two gloves, a matched pair, one for the left hand and one for the right. You place each one into a separate identical box, and without looking, you send one of those boxes to the far side of the world. You do not know which box holds which glove. But the moment you open your own box and see a left-handed glove resting inside you, instantly know with perfect certainty that the other box, thousands of miles away, holds the right-handed one. This is not a mystery. It is simple logic. The gloves were always one left and one right. Your discovery did not change anything. It only revealed what was already true. But quantum entanglement is not like this. Entangled particles are not like a pair of gloves whose identities are set from the start. They are more like a pair of gloves that do not decide which hand they belong to until the moment you open one of the boxes. And whichever one you open first, somehow in an instant, tells the other one how to be. It is not just that their fates are linked. It is that their properties, their very states of being, do not seem to exist in a definite way until the moment you measure one of them. And the act of measuring one instantly and with no delay affects the other. This is the phenomenon of quantum entanglement, and it is one of the most baffling and beautiful features of the quantum world. It works like this. When two particles are born together or interact in a certain intimate way, their quantum states can become linked. Whatever happens to one in a very real and immediate sense affects the other, even when they are separated by the width of a room, a continent, or a galaxy. Imagine two entangled particles of light whose polarization is uncertain until measured. They exist in a shared quantum state, a quiet superposition of all their possibilities. Only when you measure one does its outcome become definite. And in that very same instant, the state of the other particle becomes definite too. If you measure one photon in a quiet lab in Paris, the other photon, perhaps drifting through the silent dust of a room in Tokyo, responds at that very moment, as though the universe had just updated both of their stories simultaneously. This is what Albert Einstein once called, with a sense of quiet wonder and unease, spooky action at a distance. Einstein was not fond of spooky things. He believed in a local universe, a world where what happens in one place cannot instantly affect what happens in another. It is a cornerstone of his theory of relativity. Nothing, not even information, can travel faster than the gentle speed of light. The idea that two particles could coordinate their states instantaneously without sending any kind of signal made him deeply uncomfortable. he believed that quantum mechanics must be incomplete, that there must be some hidden information, some hidden variables tucked away behind the scenes, determining the outcomes all along, just like those gloves in the boxes. To Einstein, the universe should be orderly, predictable, and above all, local. But decades later, quiet experiments began to confirm what the strange mathematics had predicted all along. Entanglement is real, and those hidden variables, they have never been found. In the 1960s, a physicist named John Bell devised a beautiful mathematical test that could tell the difference between the predictions of quantum theory and the predictions of a world with hidden information. And when the quiet experiments were done again and again, with ever greater precision, the universe whispered the same answer. The spooky connection was real. Entangled particles behave in ways that cannot be explained by any local predetermined story. Their results are random, yet perfectly mysteriously in sync. It is as if they share a private script, one that remains unwritten until the curtain rises, and then they improvise their parts together with an eerie, perfect timing. Still, this does not mean we can use entanglement to send messages faster than light. That would break the fundamental rule of cause and effect, and nature in its wisdom prevents this. While the entangled particles do respond to each other's measurements instantly, the outcomes of those measurements are themselves fundamentally random. You cannot control what result you will get when you measure your particle, which means you cannot encode a message in it. It is like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow when one person's coin lands on heads, the other person's always lands on tails. They are not sending messages. They are just in sync in a way that seems to defy space. What is truly strange is that this connection does not seem to weaken with distance. You could separate two entangled particles by light years, and the bond would remain unbroken. There is no known limit. Physicists have now entangled particles over hundreds of kilometers using satellites, and the results continue to hold. So what is this connection? Is it a kind of invisible thread woven through space? A shared identity that distance cannot break? A subtle form of information smeared between two places at once? The truth is, no one is completely sure. Some see entanglement as a reflection of a deep, non-local fabric to reality. Some have even whispered that this entanglement, this quiet connection, is not something that happens in space, but is the very thing that holds space together. That the geometry of the universe itself might emerge from a vast network of these silent quantum links. And like so many quantum ideas, this is not just a philosophical dream. Entanglement is the foundation for technologies that are slowly coming into being. It is the basis for quantum teleportation, not of people, but of the delicate quantum states of particles, a whisper of information sent from one place to another. It is the heart of new forms of cryptography, where a message can be sent with a perfect guarantee of privacy. So this spooky action, once a source of deep unease, is now a cornerstone of our future. It reminds us that the universe is not just a collection of separate lonely things bouncing around in a void. It is a deeply connected web where even the most distant parts can be woven into a shared single whole, where separateness at times is a beautiful illusion. And in this interconnected world, even a simple thought experiment about a cat takes on a new and deeper meaning. There are few creatures in the world of science more famous or more misunderstood than Schrödinger's cat. This quiet, curious feline has become the soft mascot of quantum physics, a creature trapped not in a real box, but in a thought experiment so peculiar that it feels like a dream, or perhaps a gentle satire. And in a way, it is. It was never meant to be taken literally. But like all good metaphors, it touches upon something deeper, a quiet discomfort at the heart of this new quantum world. The story began in the 1930s, a time when physicists were gently wrestling with what quantum theory truly meant. The math worked, the predictions were flawless, but what was it saying about the world? Was the wave function, that shimmering cloud of possibilities, a real thing? Did particles truly exist in multiple states at once, until the moment they were measured? Erwin Schrödinger, the very man who gave us the elegant equation for the wave, was skeptical. He felt a quiet unease with how far some were willing to push the idea of superposition, especially when it came to the moment of measurement. In his view, there was something unsettling about applying the same strange rules that governed a single tiny electron to the everyday objects we know and love. Objects like, for instance, a cat. And so he posed a question, a dark and playful question. What happens if you take the quiet weirdness of the quantum world and you scale it up to something you can hold in your arms? Imagine, he said, a sealed box, a space entirely cut off from the world. Inside is a cat, and alongside the cat there is a tiny single radioactive atom. There is also a Geiger counter, a quiet listener, and a small vial of poison connected to a trigger. The fate of the cat is now woven together with the fate of the atom. If the atom decays, an event quantum mechanics tells us happens at a purely random moment, the Geiger counter will detect it. The trigger will be released, the vial will break, and the poison will be released. But here is the gentle quantum twist. The theory tells us that, until we observe the atom, it exists in a superposition of states. It is both decayed and not decayed at the same time. And if the atom is in a superposition, then the entire system, woven together by this delicate thread of fate, must be in a superposition as well. The detector, the poison, and yes, the cat. The cat is both alive and not alive. Not as a metaphor, not as a possibility, but according to a literal reading of the math in a true and physical state of both at the same time. Of course, no one has ever performed such an experiment. Schrödinger was not proposing a cruel test. He was making a point. He found it absurd to think that a cat, a creature of warmth and whiskers, and a clear preference for naps, could exist in such a blurry, undefined state. It wasn't just strange, it felt like nonsense. And yet, the idea has remained with us because it captures the very essence of this quantum mystery in a single, unforgettable image. A cat that is both here and gone until the box is opened. It is a powerful way to feel what it means for a system to remain unmeasured. It is not about indecision. It is about possibility. Until the act of observation collapses, the wave function the system holds within it every outcome, every future, all at once. Schrödinger's cat is not really about a cat. It is about what we are allowed to say about the world before we have looked. In the quantum world, the act of observation seems to play a central, almost magical role. Before you measure a system, it exists as a cloud of probabilities. But the moment you interact with it in a way that reveals information, that cloud collapses. The system chooses a state. One possibility becomes real. All others softly fade away. But here is the quiet, nagging question at the heart of the story. What exactly counts as a measurement? Is it the presence of a conscious human observer? Is it the click of the mechanical detector? Is it a single photon of light from the outside world leaking into the box and interacting with the system? The theory, in its elegant precision, is oddly silent on this point. It does not define the line, and that is why the cat is still so important. It forces us to sit with this gentle ambiguity. Different ways of dreaming about the universe offer different answers. One view, the Copenhagen interpretation, gently suggests that we should not worry about it. The wave function is a tool that tells us the probabilities, and the question of what is real before we look is simply not a meaningful one to ask. Another view, the many worlds interpretation, offers a more radical story. It says the wave function never collapses at all. Instead, the entire universe splits. In one branch, the cat is alive. In another parallel branch, it is not. Both outcomes are real, each in its own separate world. And a third idea, known as decoherence, whispers that a system as large and warm and complex as a cat can never truly remain in a perfect superposition anyway. It is constantly interacting with its own environment, the air in the box, the warmth of its own body, and these countless tiny interactions effectively wash away the quantum strangeness, leaving behind what looks like a single classical reality. Each of these views carries its own kind of poetry, its own philosophical weight. But they all circle this same quiet mystery. The box is not just a container, it is a boundary, a soft line drawn between the shimmering quantum world of possibility and the solid classical world of definite outcomes. The cat in the box is a metaphor for all unmeasured things. An electron traveling from one point to another does not take a single path. It spreads out, exploring every possible route at once, until we look and its journey resolves into a single story. The difference is only a matter of scale, not of principle. And that is what so deeply troubled Schrödinger. If the theory truly applies to everything, then at some level, everything, including ourselves, is part of this vast, shimmering superposition. And so we are left in the quiet of the unopened box, with the gentle weight of a question that has no simple answer. And in that quiet, we are reminded that certainty is rare, clarity is conditional, and sometimes the universe waits for us to peek inside. But in this world of shimmering possibilities, even the most solid of barriers, the walls of the box itself, are not always what they seem. In our everyday world, a wall is a simple, honest thing. If you gently toss a ball of yarn at a solid wall, it will bounce off. It follows the rules. It does not have enough energy to pass through, and so it does not. The universe says this far and no further, and the yarn obeys like a well-behaved and gentle object. But in the quantum world, predictability takes a soft and gentle holiday. In this strange and shimmering realm, a particle can drift toward a wall, a barrier of energy it does not have the strength to cross. And yet, a moment later, it can appear on the other side. There is no smashing, no breaking, no squeezing through some unseen crack. It simply arrives, as if it decided the obstacle was not quite as solid as it looked, as if the wall was only a suggestion. This quiet, impossible journey is called quantum tunneling, and it is one of those effects that makes you feel as though the laws of physics are dreaming. But this is a very real dream. It is measurable, it is predictable in its own strange way, and it is fundamental to how the universe breathes and changes. And surprisingly, it all comes down to the soft, shimmering nature of probability. To understand this gentle miracle, we must return to the idea of the wave function, that soft, hazy cloud of possibility that describes where a particle might be. In the quantum world, a particle like an electron is not a simple hard dot. It is a spread of potential. And this wave of possibility can stretch across space, fading gradually like a whisper instead of stopping all at once. This means that even if there is a place, the particle technically should not be able to reach its wave function, might still stretch into that forbidden zone, however faintly. Now imagine that particle, that soft wave of maybe, approaching a barrier. In the solid classical world, this would be a hard stop. The journey would end. But the quantum wave function does not vanish at the barrier. It tapers off like a soft echo fading through a wall. And if that wall is not too wide, or the barrier not too high, that gentle whisper of a wave can make it all the way to the other side. The particle might not have the energy to climb over the wall, but its wave of possibility can tunnel through. And if a part of that wave makes it to the other side, there is a small but very real chance that the particle itself will simply appear there too. It is not magic. It is a quiet kind of mathematics. This idea, as soft and abstract as it feels, has consequences that shape our entire universe. Think of the slow, patient process of radioactive decay. Some atoms are unstable, their hearts holding too much energy. And one of the ways they find their way to a state of calm is by releasing a particle. But these particles are trapped inside the atom's nucleus by a powerful, invisible barrier. According to the old rules, they do not have enough energy to escape. They should be trapped forever. And yet, they do escape, all the time. Quantum tunneling is the reason why. Inside the nucleus, the particle's wave function stretches, reaching toward the edge of the barrier. Even though it is unlikely, there is always a tiny persistent chance that the particle will tunnel through. Over long stretches of time, that small probability adds up, and eventually, the particle pops out. That is radioactive decay, a quiet quantum escape. Without tunneling, the world as we know it would be a very different and much more stable place. Tunneling is also at the heart of the most important fire in our universe, nuclear fusion. In the center of our sun and in the hearts of all the stars, hydrogen atoms are crushed together under immense heat and pressure. But even in those extreme conditions, they do not have quite enough energy to overcome the powerful repulsion that exists between them. According to the old classical story, fusion should barely happen at all. And yet, the stars shine. Tunneling explains why. In the fierce dance at the center of a star, particles get close enough for their wave functions to overlap. And in that moment of closeness, there is a tiny chance that one will tunnel through the wall of repulsion and fuse with another. Multiply that tiny improbable chance by the unthinkable number of particles in a star, and you get a brilliant, steady, and life-giving fire. The gentle warmth of sunlight on your skin is the echo of a trillion quantum tunnels happening right now millions of miles away. And it is not just in the distant hearts of stars that we find this gentle trick at work. We use it right here on Earth. There is a device, an elegant and wondrous tool called a scanning tunneling microscope. It allows us to see the world at the level of individual atoms. It works by bringing an incredibly sharp-pointed tip extremely close to a surface hovering just a few atoms away. At that tiny distance, electrons can do something remarkable. They can tunnel across the empty space between the tip and the surface. By measuring the quiet flow of these tunneling electrons, the microscope can build a breathtakingly detailed map of the atomic landscape. What is so wondrous is that the microscope never touches the atoms it is imaging. It relies entirely on tunneling on the quiet ability of electrons to slip through a barrier of empty space. This soft, non-contact touch allows us to see the very texture of matter itself. At its core, tunneling teaches us something profound about the nature of reality. We often think of the world as being made of hard boundaries. A particle can go here, but not there. A wall is a wall. But the quantum world is softer, more nuanced. Barriers are not absolute. They are probabilistic. They are suggestions, not commands. And because of this gentle rule, particles are not confined to the straight, predictable paths we imagine for them. They can cheat. They can slip through the cracks in logic. They remind us that the universe is not a machine made of perfect, rigid gears, but a shimmering tapestry of likelihoods and possibilities. The heavy, solid wall still stands, but for the electron, for the particle of light, for the tiny dancers in the heart of a star, that same wall is sometimes only a mist, a shadow, a gentle invitation to take a shortcut. And in this world, where even solid walls can dissolve into mist, what then is the nature of emptiness itself? In our everyday life, we think of nothing as, well, nothing. The absence of things. An empty room, a blank page, the quiet, dark space under the bed where socks mysteriously disappear. And when we think of the vastness of space, we often picture a perfect void, a cold and silent expanse with absolutely nothing in it. But in the quantum dream, nothing is never truly empty. What we call the vacuum is in fact a restless, jittering stage. It is not filled with atoms or light or sound, but it is far from blank. Even when all the particles have been swept away and no fields are actively doing anything, the vacuum still seethes with a quiet, shimmering energy. On the smallest of scales, space is alive with an invisible activity. Waves rising and falling, particles flickering in and out of existence. It is like the hum beneath the silence, the soft glow that remains behind the darkness. And it all begins with uncertainty. Heisenberg's quiet principle does not just apply to a particle's position and its motion. It also applies to energy and to time. This means that even in a region of space where the energy should be zero, it can gently fluctuate. For the briefest of moments, energy can be borrowed from the future as long as it is paid back almost instantly. These soft, shimmering fluctuations of energy give rise to what are known as virtual particles. They appear seemingly from nowhere, exist for a fleeting, borrowed moment, and then vanish as if they were never there at all. They are called virtual, not because they are imaginary, but because their existence is too brief to be observed directly. They are the ghostly visitors of the vacuum, the quiet whispers in an otherwise empty room. And yet these quantum blips, these fleeting guests, have very real and measurable consequences. One of the most beautiful and strange examples of this is a phenomenon known as the Casimir effect. It is one of those rare moments where we can almost see the quantum vacuum doing something tangible. It works like this. Imagine placing two very thin, perfectly smooth metal plates, like two perfect mirrors, extremely close together in a perfect vacuum. so close they are almost touching, separated by only a few nanometers. According to the old classical physics, nothing should happen. There is no air between the plates, no obvious forces acting upon them, just an empty, silent gap. But quantum mechanics tells a different story. Because the space between the plates is so very small, only certain wavelengths of virtual particles are allowed to exist there. Only the ones that fit neatly between the two boundaries. Outside the plates, however, in the vast ocean of the vacuum, there is no such restriction. All possible wavelengths, all possible whispers of virtual energy can exist. The result is a gentle imbalance. There is slightly more pressure from the chorus of virtual particles on the outside of the plates than from the quiet hum of particles on the inside. And this imbalance creates a soft, steady force that gently pushes the two plates together. That is the Casimir effect. It is a tiny, delicate force, but it has been measured. In quiet, careful laboratory experiments, scientists have watched these plates drift toward each other exactly as the quantum theory predicts. It is as if the vacuum itself is gently squeezing them as soft and tangible proof that even nothing has a kind of substance. This quiet energy of empty space is not just for quirky lab experiments. It plays a role across the entire universe. In the vast, dark expanse of cosmology, there is an idea that this vacuum energy might be the mysterious breath that is causing the universe to expand at an ever-increasing rate. A force we have named dark energy. And while we do not yet understand it, the concept of a quantum vacuum buzzing with a life of its own may be a large part of the puzzle. But there is a deep and humbling mystery here. The amount of energy that our theories predict for the quantum vacuum is enormous, wildly, impossibly larger than what we actually observe in the cosmos. It is a discrepancy so vast it has been called the worst prediction in the history of physics. And no one has quite figured out why. It is a quiet reminder of how much of the story is still unwritten. Back at the soft quantum scale, these virtual particles also play a supporting role in other strange and beautiful phenomena. In the dance of light and matter, the force between charged particles is mediated by the constant exchange of virtual photons. These gentle messengers flickering between existence are the conversation that we call the electromagnetic force. Even the solid, steady mass of a proton is in part the result of a shimmering, energetic swarm of virtual quarks and gluons flickering and dancing inside it. What we think of as stable, solid matter is really the result of a constant flickering dance with this invisible, fluctuating vacuum. And while these particles appear and disappear faster than we can ever hope to measure, their influence is woven into the very fabric of everything. They gently alter the energy levels of electrons in atoms. They are part of every interaction in nature. In a way, the quantum vacuum is the most fundamental field of all. It is the stage upon which everything else unfolds. Every other field, electromagnetic, gravitational, nuclear, exists within it. They ripple and hum against its background, like instruments playing on top of a bass line that never ever stops. It is humbling to think that nothing is never truly nothing, that even in the most apparent stillness, the universe teems with a hidden, gentle activity. In the pauses between moments, in the gaps between particles, in the deep and profound silence between the stars, something is always happening. We live not on a quiet stage, but but on one that murmurs softly beneath our feet. And while we may not hear it with our ears, we are learning how to listen. The vacuum hums, the particles flicker, and reality dances to a rhythm we have only just begun to understand. And on this restless, shimmering stage, a final, profound mystery unfolds. The moment a single possibility becomes real. In the quantum world, reality does not always behave like a story with a clear and simple path. Particles do not travel in straight lines, but drift in soft clouds of probability. They exist in many states at once. They link themselves together across vast distances, and they can whisper their way through walls that should be solid. But perhaps the most profound and quiet mystery in this entire quantum tale comes when we ask a very simple, very human question. What happens when we look? This simple act of observing, of measuring, of gently asking the universe, "Where are you?" seems to trigger something dramatic. A sudden and irreversible shift, a change in the very nature of what is real. This moment, this quiet and mysterious event, is known as the collapse of the wave function. Before this moment, a particle like an electron or a photon is described by its shimmering wave function. That mathematical cloud that holds all the possible outcomes of where it could be or how it might be moving. The electron is not in one single place. It is in a soft and gentle blend of many possible places. Its spin is not up or down. It is both. Its path has not yet been chosen. It is all of them at once. The wave function is a shimmering, probabilistic fog. But then you measure it. You turn on your detector. You ask the question. And in that instant, the wave function collapses. The soft fog of possibility condenses. All those swirling potential futures snap into a single present reality. The electron is suddenly there in one precise and definite spot. Its spin is now up or down, not both. And this collapse does not seem to happen slowly. It is not a gradual fading of the other possibilities. It is abrupt, binary. One moment, the universe holds a superposition of all stories. The next, it has chosen one and locked it into place. As if, after a long and thoughtful hesitation, reality makes a final decision the very moment we check. That is strange enough on its own. But it gets stranger, because no one knows exactly what causes the collapse. Is it the physical touch of the measuring device? Is it the quiet transfer of information from the small world to the large one? Is it the presence of a conscious mind, a human observer that finally breaks the spell? A camera, a computer, a single fly buzzing past the experiment. The truth is the collapse of the wave function. Though it is a central and necessary part of the quantum story, is not understood. It may be the biggest and quietest mystery in all of modern physics. Different ways of seeing the universe offer different gentle answers to this question. The most traditional view, the one known as the Copenhagen interpretation, suggests that the wave function is not a real physical thing. It is simply a tool, a mathematical recipe for predicting probabilities. And the collapse is what happens when we gain knowledge. Before that moment, asking what is really happening is not a meaningful question. The electron was not hiding somewhere waiting to be found. It simply was not anywhere in particular until we looked. It is a practical and useful approach, but it leaves the heart of the mystery untouched. It does not explain what a measurement truly is, or why the universe must play by this strange rule at all. Then there is a more wondrous and perhaps more unsettling idea: the many worlds interpretation. This view throws the idea of collapse away completely. It suggests that the wave function never collapses. Instead, every single possible outcome actually happens, just not in your universe. When you measure an electron's spin, the universe itself gently splits. In one branch of reality, you find that the spin is up. In another, a version of you finds that it is down. You only experience one of those outcomes, but the others are just as real, unfolding in parallel silent worlds. There is no collapse, no mystery of a chosen outcome, just a constantly branching tree of realities. It is a bold and beautiful idea, and it follows the mathematics perfectly. But it comes at the cost of imagining a cosmos filled with a near infinite number of unseen parallel selves. Other ideas try to make the collapse feel more real, less mysterious. They suggest that the wave function is a physical thing and that it collapses on its own spontaneously without any need for an observer. In these stories, nature itself is rolling the dice all the time, and a measurement simply increases the chance that a collapse will happen. And then there is a newer, softer view. One that suggests the wave function does not describe the universe at all. It only describes our own personal beliefs about the universe. It is a subjective map of what we know. And the collapse is not a physical event out there in the world. It is a mental one happening inside our own minds. The moment we learn a new fact, our map of possibilities updates. Reality does not change. We do. And so we sit more than a century after this quantum dream began, and the collapse of the wave function remains a ghost in the machine. The math works with a beauty and a precision that is breathtaking. We can predict the outcomes of experiments with an accuracy that is almost beyond belief. But what is it that collapses? When does it happen? And why is the collapse even real? Or are we just seeing the soft and gentle limits of our own understanding? You can think of the collapse as the moment the quantum world tips over into the classical world we know. A kind of phase change, like steam condensing into water or water freezing into solid ice. But unlike with water, the rules for this transformation are misty and undefined. We do not know the temperature. We do not know the pressure. We just know that at some point the soft fog of possibility becomes a definite shape and maybe becomes is. It is a quiet reminder that the deepest questions in science often lead us to the edge of philosophy. Is the universe fundamentally probabilistic? Is reality dependent on who is looking? Is it shaped by information, by consciousness, or by something we have not even begun to dream of yet? The dream deepens and we drift with these quiet, unanswered questions. If quantum physics had a quiet hometown, a place where its strangest and most profound ideas first learned to breathe, it would likely be Copenhagen. A city of quiet canals and gentle light. A place where in the early 20th century, a new way of thinking about the universe began to take hold. At the heart of this story is a gentle mind named Niels Bohr, a Danish physicist with a taste for long, thoughtful sentences. He helped to shape one of the most enduring and most debated views of the quantum world, a perspective that has come to be known as the Copenhagen interpretation. The idea in its essence is deceptively simple. In fact, that is part of its quiet and lasting power. In this way of thinking, the universe holds its breath. A quantum system does not have definite properties until the moment it is measured. An electron does not have a fixed position. A photon does not commit to a particular path. A particle does not choose a state until the gentle act of observation forces it to. Before that moment, reality is a soft and shimmering cloud of possibilities, a probability wave. The act of looking does not simply pull back a curtain on a scene that was already set. It is more like the final gentle brushstroke that completes the painting. The measurement does not just reveal something that was already there, it creates the outcome. In other words, reality is not quite real until we ask it to be. That is a bold and wondrous statement, the kind of thought that makes the mind grow still. But Bohr and his colleagues were not trying to make the universe mysterious for the sake of it. They were trying to make sense of what the quiet experiments were telling them. Every time they tried to imagine particles as tiny, solid billiard balls, the math would fall apart. But when they treated them as waves of probability waves that only resolved into a single point upon measurement, everything clicked into place. The wave function in this view is not a physical thing. It does not describe a particle's actual hidden location. Instead, it is a soft collection of whispers about what we are allowed to know. It is a gentle guide to what might be, not a map of what is. And this leads to one of the most profound claims of the Copenhagen interpretation. Questions about a system's state before it is measured are simply meaningless. Asking where the electron was before you looked for it does not make sense. Because where only becomes a meaningful concept after the measurement has taken place. Reality is not something you peel back layer by layer to find a hidden core. It is something that snaps into focus the very moment you look. It is not that the particle was hiding its true nature. It simply did not have one yet. Understandably, not everyone found this idea comforting. Albert Einstein, for one, was famously uneasy. He wanted a universe that existed on its own terms, independently of whether anyone was observing it. He believed in an underlying reality objective and predictable, a clockwork that hummed along, whether anyone was there to listen or not. To Einstein, the Copenhagen view sounded like saying, "The moon does not exist unless you are looking at it." Bohr did not try to offer a grand metaphysical solution to this puzzle. Instead, he embraced a kind of pragmatic and gentle ambiguity. His view was that quantum theory tells us what we can say about nature, not necessarily what nature is. The role of science in this quiet dream is not to uncover the ultimate truth of what is out there, but to describe the outcomes of our interactions with the world as precisely as possible. If that sounds a little unsatisfying, you are not alone. The Copenhagen interpretation is often described as more of a prescription than a description. It tells you how to use the strange new equations. It tells you with breathtaking accuracy what the outcomes will be. But it does not tell you what is actually happening behind the curtain. This gave rise to a quiet mantra, a phrase that is often misunderstood. Shut up and calculate. It was not a quote from Bohr himself, but it captures the mood. The idea was, stop wrestling with the ghost in the machine. Stop worrying about the deep philosophical implications and simply use the theory. It works. It gives the correct predictions. Isn't that enough? And to be fair, this approach does work. It is the default way of thinking that is taught in countless classrooms and used in laboratories all over the world. It is the foundation upon which we have built semiconductors, lasers, and the dawn of quantum computers. It has never, not once, failed an experimental test. For many, That quiet, perfect track record outweighs any philosophical discomfort. But still, the discomfort lingers. If reality only becomes real when it is measured, what does that say about the universe before any observers existed? Did the early universe exist in a kind of suspended dream, a shimmering cloud of possibilities, waiting for a mind to arrive and collapse it into form? Most physicists would say no. The Copenhagen interpretation does not require a conscious human observer, just an interaction. A measurement in this context is any process that pulls a single thread of information from the quantum tapestry, forcing the system to pick a side. But even this leads to more quiet questions. What counts as a measurement? At what point does the shimmering wave collapse? And why does the universe follow this strange and gentle rule at all? The Copenhagen view tends to answer with a soft shrug of the shoulders. The theory does not explain why the collapse happens. It just says when. If you want a deeper story, a dream with more detail, you will have to look elsewhere. And many have. Other ways of dreaming about the universe, with names like many worlds or pilot wave theory, all try to offer a more complete picture. Each one tries to hold on to some piece of our classical intuition that reality exists on its own, that cause leads to effect in a straight line. But each of these other dreams comes with its own strange and wondrous complications. The Copenhagen view, by contrast, is lean. It does not invent hidden information. It does not multiply universes. It just lays out a set of quiet, workable rules. And perhaps that is its deep and lasting appeal. In a field of physics filled with shimmering, endless possibilities, it offers a kind of calm. It is not trying to solve every mystery. It is content to simply describe the world we can see and measure and interact with, without claiming to know the deeper machinery that hums beneath it all. Bohr himself understood that this new world was not meant to be comfortable. He once said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." He knew that the Copenhagen approach was not about making peace with reality. It was about making peace with uncertainty. It invites us to accept the strangeness to work within it, without demanding that the universe explain itself in words we already understand. It is not a final answer. It is a quiet rulebook, a gentle reminder that in the quantum world, simplicity and discomfort often walk hand in hand. And yet, this is only one way to dream about the world. Other stories, other paths were already branching in the quiet. Imagine for a moment that you are holding a single coin between your fingers. You flip it. It spins through the quiet air, a glimmer of silver in the soft light, and lands with a gentle clink. Heads. But according to one interpretation of the quantum dream, something else happened in that very same moment. Somewhere, not here, but just as real, the same coin landed tails. And somewhere else, again in another quiet branching of the world, it landed perfectly on its edge and rolled softly under the couch. Every single possible outcome of that simple flip unfolded, not as a maybe, not as a probability, but as a real and tangible branch of reality. And you just happened to find yourself in the one that saw heads. This is the strange and beautifully simple idea behind the many worlds interpretation of quantum physics. It began as a quiet thought, an alternative way of looking at that old and stubborn mystery of the wave function collapse. You may remember the wave function, that shimmering mathematical cloud that holds all the possibilities of a quantum system. In the traditional Copenhagen view, when you make a measurement, that cloud collapses and one single possibility becomes real. But what if it never collapses at all? In 1957, a physicist named Hugh Everett III proposed a radical and gentle idea. Maybe the wave function is always evolving smoothly. Maybe it never breaks, never snaps into a single state. Maybe when you measure a system, you do not force it to choose a single outcome. Instead, you split. The universe splits. Every possible outcome of your measurement plays out, but each one unfolds in its own separate parallel branch of reality. It sounds like a story from a dream, a journey into science fiction. But Everett was not writing a novel. He was doing mathematics. And his version of quantum mechanics is mathematically identical to the standard one, just without the extra mysterious rule that says a collapse must happen when you look. In his quiet, elegant view, the wave function never collapses. It only branches. It works like this. Imagine an electron with two possible spin states up and down. If you measure its spin, the traditional story says the electron is in a superposition of both states until you look at which point it chooses one. Everett's story is different. It says there is no choosing necessary. Instead, the very act of measurement causes you, the observer, and the electron to become entangled. The whole system splits into two correlated branches. In one branch, you observe the spin is up. In the other, a version of you observes the spin is down. Both outcomes are real. Both versions of you are real. Each exists quietly and completely in a different branch of the universe. There is no randomness, no mysterious collapse. Just a growing, branching tree of reality. This may sound like a recipe for a universe filled with an infinite number of parallel selves, a cosmos overflowing with doppelgangers. But the many worlds interpretation does not rely on fantasy. It does not propose new kinds of physics or untested forces. In fact, its central appeal is its simplicity. It sticks only to the mathematics we already have. It simply refuses to add the extra strange assumption that something magical happens when we look. To those who find this view comforting, this is its greatest strength. The idea is wondrously strange, but the math is clean. Of course, not everyone is comfortable with this. If the universe is constantly branching into new realities, where do all of these other worlds go? Are they stacked on top of each other, floating in some higher unseen dimension? The theory does not say. And that is part of its quiet philosophical tension. Many worlds is not a theory about the structure of space. It is a statement about how quantum systems evolve. The other branches are real, but they do not interact with our own. Once a split occurs, the branches are said to decohere. They no longer interfere with each other. They become, for all practical purposes, invisible and unreachable. This makes the theory very difficult to test directly. After all, if we cannot see or touch or communicate with the other branches, how can we ever know they are there? This is the central gentle criticism. Many worlds may be elegant, but is it science? Can you prove it wrong? Supporters of this view would say, that is the wrong question. It is not about adding new predictions. It is about not adding unnecessary assumptions. If the math of the wave function evolves smoothly, and that math never includes a collapse, then why should we assume a collapse exists at all? But let us take a quiet moment to imagine the scale. Every single time a quantum interaction has more than one possible outcome, the universe branches. This is not just happening in quiet physics labs. It is happening in every molecular collision, every radioactive decay in the heart of the Earth, every single photon of starlight that strikes a leaf. The universe is not just splitting every now and then. It is branching constantly, exponentially, unimaginably. But in the same way that we do not feel the Earth spinning beneath our feet, we do not feel this branching. To us, it is invisible, seamless. We simply find ourselves on one path and experience one outcome as if that is all there ever was. It is also important to say that in the many worlds, these other realities are not parallel lives in the way we might imagine from stories. You are not hopping between them. You do not get to meet your other selves. Each branch is causally isolated. There is no communication across the gentle divide. No peeking at the other versions of yourself who chose the soup instead of the salad. Once a split happens, it is permanent. This avoids many of the difficult questions that come with the collapse of the wave function. There is no need to define what counts as a measurement, or to wonder when exactly reality becomes real. Everything is always real. Everything is always evolving smoothly. But that calm mathematical elegance also comes at a cost. If every possible outcome happens, then why does it feel to us like only one thing occurred? Why does probability even mean anything? The many worlds view redefines probability. It is not the chance that something will happen, but a measure of how many of you, how many future selves end up in each branch. It is a subtle and difficult shift in thinking. But then none of this quantum dream is built upon our everyday intuition. And despite all its strangeness, this idea of a branching universe has inspired deep and serious thought. Some believe it may offer a path toward unifying quantum mechanics with the gentle, curving world of gravity. Others see it as the natural way to understand quantum computing, where a machine performs its calculations across a vast number of these parallel states at once. It also offers a unique kind of comfort, or perhaps a profound disquiet, depending on your view. In this interpretation, no possibility is ever truly lost. Every outcome, every path not taken still exists somewhere. The decisions you did not make, the chances you did not take, they are all still out there, playing out in their own quiet timelines. Not just as hypotheticals, but as real physical events in real physical worlds. It is not meant to make you feel small. If anything, it is a reminder that the universe may be more generous, more full of stories than we ever imagined. Not just a single narrative unfolding in a straight line, but a vast and shimmering library with every possible story inked into existence. So when you think of many worlds, do not picture a noisy, chaotic stack of realities. Picture a quiet branching tree, each twig a path, each leaf a world, each outcome a soft and gentle poem written in the language of physics, and all of them, in their own way, true. And from this vision of branching worlds, we drift even deeper to the very fabric of existence itself. Imagine pulling back the final gentle curtain, the curtain that separates our world of things and places from the deeper reality that lies beneath. Imagine looking past the stars, past the oceans, past the quiet chair you were sitting in, past your own hand resting in your lap. What if all of it all matter, and all energy was not made of solid things at all? What if the most fundamental stuff of reality was not stuff at all, but vibrations? Soft, invisible ripples spreading through fields that fill every single corner of space. Welcome to the quiet and profound world of quantum field theory. A dream where the universe is not built from tiny solid particles, but from endless shimmering fields that hum beneath everything. Let us begin this thought gently. In the old classical way of seeing a field is something that exists everywhere in space, assigning a value to every single point. A familiar example is a magnetic field, an invisible presence that tells a compass needle which way to turn. The field is there whether the needle is or not. It is smooth, continuous, and fills the world like an invisible, gentle current. Now, quantum mechanics comes along, and it sprinkles its soft layer of uncertainty onto this picture. It says that these fields do not just sit there quietly and smoothly. They fluctuate. They buzz with a restless, random energy, even in the complete absence of any real particles. Every field, electric, magnetic, gravitational, is quantum in nature. It jiggles and shimmers even when it seems to be perfectly empty. And here is the wondrous leap of this new dream. In quantum field theory, or QFT, everything is a field. Every particle you have ever heard of, the electron, the photon, the quark, is just a little blip, a tiny localized ripple in its own corresponding field. A particle is not a tiny marble flying through space. It is a concentrated, quantized wiggle in an underlying field that fills all of reality. Let us think of the electron. The theory says there is an electron field that exists everywhere, in every point of space and time. When you see an electron, you are not looking at a separate self-contained object. You are observing a specific localized excitation of that field. The field in that one small spot became excited, and that little ripple of energy is what you call an electron. Now, the same is true for a particle of light, a photon. There is an electromagnetic field that fills all of space. When a photon zips past, it is not a tiny bullet of light. It is a ripple, a tiny quantized vibration in that electromagnetic field. Change the frequency of that ripple, and you get a different color of light. Make the ripple stronger, and you get a brighter light. But it is all just different ways of dancing in the same single field. There is a field for every known fundamental particle. Quark fields, gluon fields, a Higgs field. And each one of these fields permeates the entire universe, overlapping and interacting with all the others. So where did our old friend the particle go? In a sense, particles are a useful and beautiful fiction, a way for us to talk about the behavior of these fields in certain specific situations. When a field becomes excited in a very localized way, and that little ripple of energy behaves as a single discrete packet, it is convenient to call it a particle. But that is just our human label for a particular kind of behavior. The field is the fundamental reality. The ripple is what we see. This shift in perspective is profound. It turns the universe from a collection of tiny, separate building blocks into something more like a vast and silent symphony. An infinite orchestra of overlapping fields, with reality itself emerging from their gentle interference and quiet harmony. This way of dreaming also explains some of the most puzzling features of the quantum world. For instance, how is it that particles can be created and destroyed in high-energy collisions? Simple. They are just excitations of a field. If you pour enough energy into a small region of space, you can jiggle a field hard enough to spawn a new lasting ripple. That is how new particles can emerge from what seems to be thin air. And what about their mysterious twins, the antiparticles? In quantum field theory, an antiparticle is just another kind of ripple, another mode of excitation in the very same field, just with opposite properties. nothing spooky, just more symmetries in the shimmering, rippling dance. Here is a particularly elegant thought. Forces themselves are also the result of these fields. The electromagnetic force, the gentle push and pull between charged particles, is the result of those particles exchanging photons' ripples in the electromagnetic field. The strong nuclear force, the unbreakable glue that holds the hearts of atoms together, is the result of particles called gluons, vibrating in the gluon field. Even empty space, as we have seen, is not truly empty. The fields are always there, humming with a quiet baseline energy. These are the vacuum fluctuations, the source of those virtual particles that flicker in and out of being. There is something wonderfully serene about this picture. The idea that space itself is not a passive, empty stage, but an active, vibrant participant. Every single point in the universe is alive with potential. Every particle, every interaction, every beam of starlight is just a field expressing itself. Even mass, that stubborn, weighty quality of matter, is in this dream an emergent feature of a field. There is a field that permeates all of space, known as the Higgs field. Particles that interact with this field feel a kind of resistance, a gentle drag as they move through it. And that resistance is what we perceive as mass. The more resistance a particle feels, the more massive it appears to be. So, here we are, nestled in a world made of fields. You, as you listen to these words, are a delicate and complex pattern of excitations in the electron field, the quark fields, the photon field. Your thoughts are patterns of ripples. The very atoms of your body are stable, harmonious notes in this cosmic meshwork of fields, all humming in an invisible, silent harmony. You do not end at your skin. The fields that define you spill out softly into the universe. There is no sharp edge, no hard boundary, just softer or stronger ripples, fading into the broader shimmering sea of quantum reality. Quantum field theory does not just describe the universe. In a sense, it is the universe. Or at least, it is the most beautiful and complete map we have drawn so far. A map where reality is not made of things bumping into each other, but of fields interwoven in a dance too fast, too subtle, and too beautiful for our senses to ever fully catch. And as we drift in this sea of fields, a list of all its known ripples begins to emerge. A quiet accounting of all the fundamental notes in the symphony. If the universe came with a gentle, quiet cookbook, a list of all its fundamental ingredients, that recipe would be what we now call the standard model of particle physics. It is a surprisingly simple list, elegant in its organization, and just a little bit whimsical in its naming conventions. For all its soft quirks, this model is one of the most successful and well-tested stories in the history of science. It tells us what the universe is made of. It tells us how those fundamental parts interact. And it helps us understand why the world we see looks and behaves the way that it does. Let us begin by gently meeting the cast of characters. At its heart, the standard model is a collection of elementary particles. Particles that, as far as we can tell, cannot be broken down into anything smaller. They are the fundamental building blocks, the soft and shimmering notes from which all of matter and force are composed. There are three broad, quiet families: the quarks, the leptons, and the bosons. First, the quarks. These are the particles that make up the solid, steady core of atoms. They are the stuff of protons and neutrons. There are 6 different types or flavors of quarks, and their names are up, down, charm, strange, top and bottom. Yes, Those are their actual names. Physicists, it seems, can perform the most precise and complex mathematics imaginable. But when it comes to naming things, a certain gentle poetry takes over. The up and down quarks are the lightest, and by far the most common. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up. This means that almost everything you can see and touch, the chair you are in, the air you are breathing, your own body is made almost entirely of up and down quarks bound together in a quiet, stable dance. The other 4 quarks, charm, strange top and bottom, are heavier and much rarer. They are like the special guest stars of the particle world. They mostly appear in high-energy environments like the heart of a star, or in the gentle collisions of particle accelerators. They are flashy and short-lived, but they are a crucial part of the complete family. Next, we have the leptons. This group includes a particle you have met many times before, the electron. The tiny light particle that buzzes in soft clouds around the nucleus of every atom, that carries the gentle flow of electricity and that makes all of chemistry and therefore all of life possible. The electron also has heavier cousins. There is the muon, which is like a heavy, unstable electron, and the tau, which is heavier still. Like the exotic quarks, these heavier leptons do not last long in our quiet, low-energy world. Each of these 3 charged leptons also comes with a silent neutral partner, the neutrino. There are 3 types of neutrinos, 1 for each flavor, and they are the quietest, most elusive particles in the entire universe. They are incredibly light, incredibly fast, and they barely interact with matter at all. Billions of them are passing through your body right now, every single second, having traveled all the way from the heart of the sun, and they leave not a single trace. They are the gentle introverts of the cosmos, always present but rarely noticed. So far, our quiet recipe includes 6 quarks and 6 leptons. That is 12 matter particles in total, all of them ripples in their own quantum fields. But matter alone does not make a universe. We need forces, the gentle rules that govern how these particles interact with one another. And that is where the third family, the bosons, comes in. Bosons are the force carriers. Each of the fundamental forces of nature has its own messenger particle, a kind of quantum whisper that tells other particles what to do. For the electromagnetic force, the carrier is the photon, the particle of light. It has no mass. It travels at the gentle speed of light, and it is the reason that electrons are softly bound to atoms. For the weak nuclear force, which is responsible for slow and gentle processes, like radioactive decay, there are 3 bosons. And because they are very heavy, they only work over incredibly short distances inside the heart of an atom. Then there is the strong nuclear force. This is the unbreakable glue that holds quarks together inside protons and neutrons. Its carrier particle is called the gluon. Gluons are like a constant energetic exchange of whispers, a powerful bond that keeps the very core of matter from flying apart. And finally, there is the newcomer to the family, the Higgs boson. This particle was the last piece of the puzzle to be found, confirmed in quiet experiments in the year 2012. The Higgs boson is the manifestation of the Higgs field, a field that permeates all of space and gives mass to many of the other particles. Without this gentle universal field, most particles would be massless, zipping around at the speed of light, unable to clump together to form atoms or galaxies or you. So to recap our gentle story, 12 matter particles and a handful of force-carrying bosons. All of this together is the standard model. And it works with a beauty and a precision that is almost beyond belief. This simple model has predicted the outcomes of countless experiments, time and time again. It is not perfect, but it is remarkably stubbornly good at what it does. Of course, it has a few quiet, empty spaces. For one, it does not include gravity. The standard model is a quantum story, while gravity is best described by Einstein's gentle, curving classical story of general relativity. How to weave these two beautiful tales together is one of the biggest and quietest unsolved problems in all of physics. Then there is the mystery of dark matter. Our observations of the galaxies tell us that most of the matter in the universe is invisible. It does not interact with light. The standard model has no particle that can account for it. And let us not forget dark energy, that soft, mysterious breath that is causing the universe to expand. That too is a story that lies outside the pages of this book. In fact, the standard model, for all its breathtaking success, only describes about 5% of the known universe. But what a 5% it is. Every atom, every interaction, every single burst of light, every gentle breath you take, it is all contained within this shimmering, elegant lattice of particles and forces. It is the story of our world, written in the language of quantum fields. And from this grand list of ingredients, we can begin to look more closely at the individual recipes, the quiet dances between these particles, starting with the most familiar dance of all, the one between light and matter. At the quiet intersection of dazzling complexity and a soft mathematical perfection, there sits a theory that may be the crown jewel of all physics. It is called quantum electrodynamics, or QED for short. It is the story that explains with a gentle and breathtaking precision how light and matter interact. Every single flicker of a candle flame, every spark of static in a warm blanket, every gentle push and pull between the charged particles that make up our world. It is all a quiet and intricate performance choreographed by the rules of QED. And somehow this story, which involves an infinite number of possible interactions and a shimmering, mind-bending sea of probabilities, gives us final answers that match our quiet experiments with an accuracy that is almost beyond belief. We are talking about predictions that have been confirmed to better than 1 part in a billion. That is like measuring the distance from one coast of North America to the other, and being accurate to within the thickness of a single human hair. So, how does this gentle theory achieve such a quiet miracle? It begins by solving a problem that once seemed impossible. In the early days of the quantum dream, physicists knew that electrons and the electromagnetic field were in a constant, intimate dance. When an electron is gently nudged, it can release a particle of light. When it absorbs a particle of light, it can jump to a new level of energy. But trying to calculate the exact details of this dance at the quantum level turned out to be a mathematical nightmare. The equations would spiral out of control. Infinities would appear where they should not. You would try to work out the simple act of an electron releasing a single photon, and the math would whisper back a nonsense answer like infinite energy. Then a physicist with a playful spirit and a love for quiet rhythmic patterns entered the dream. His name was Richard Feynman, and he, along with others, found a way to gently tame these wild infinities. But Feynman went one step further. He made the story visual. He invented what are now called Feynman diagrams, a simple, beautiful graphical way to represent the dance of particles. They turn the most complicated quantum calculations into soft, almost childlike scribbles. In these diagrams, particles are represented by lines. Time flows gently from left to right. An electron, a straight line, might enter the scene from one side, and at some point it might release a photon, a little wavy line, and then continue on its way. That photon might then zip off and be absorbed by another electron. Or in a stranger twist, it might loop back around and be reabsorbed by the very same electron that released it. Each of these possible paths, each of these quiet stories, has its own mathematical expression. And the strange and beautiful rule of QED is that to find the right answer, you must add them all up. Not just the most likely path, but every single possible way the interaction could have happened. And that includes some very wild and wondrous possibilities. An electron emits a photon, which for a fleeting moment becomes a virtual pair of an electron and its antiparticle a positron, which then annihilate each other and become another photon, which is then absorbed by the original electron. These are the virtual particles, the ghostly visitors of the vacuum that we have met before. They exist only in the brief mathematical interludes between real measurable events. But their quiet, flickering presence shapes the final outcome in a very real and very precise way. This is where QED becomes less like a set of rules and more like a poem written in the language of calculus. It does not just account for what does happen. It accounts for everything that could happen. Every gentle zig, every soft zag, every quiet looping detour is a necessary part of the final answer. And somehow, when all of those infinite shimmering possibilities are woven together, the result is a single clear prediction. A prediction so precise, it could tell you how an electron would behave on the far side of the galaxy, down to the tiniest, quietest decimal. One of the greatest triumphs of this theory is its description of the electron's magnetic moment. The electron, in its quiet spin, acts like a tiny microscopic magnet. Classical physics can predict its strength. But the quiet hum of the quantum vacuum with all its virtual particles tweaks that strength just a little. QED calculates this tiny, gentle tweak, and the result matches the measured value to over 10 decimal places. It is not just good. It is a quiet, stunning testament to the power of this dream. The theory also explains with a soft and simple elegance phenomena like Compton scattering, where a photon gently bounces off an electron, and pair production, where a particle of pure light can transform into a pair of matter and antimatter particles. All of these processes, which sound like they belong in a world of magic, fall naturally and quietly out of the mathematics of QED. It is worth remembering that QED does not stand alone. It is the quantum field theory that describes the dance of electromagnetism. But it was also the prototype, the first completed chapter in a much larger story. The strong force has its own more complex version. The weak force has its own. But QED came first, and it set the standard for what a perfect physical theory could be. And here is something wonderfully charming. Despite its mind-bending mathematics, QED is at its heart deeply intuitive, once you get the hang of its quiet rhythm. Feynman himself often said that the fundamental rules of quantum electrodynamics could be written on the back of a napkin. In his signature gentle style, he boiled it all down to, "This particles take every possible path. You add up the probabilities for all those paths. And the final sum gives you the answer. The rest," he would say, "is just bookkeeping." This idea that nature explores every single possible route is at the very heart of the quantum worldview. An electron does not just go from point A to point B. It feels out every single path through every obstacle, around every corner, and under every bridge, all at the same time. And QED is the mathematics that allows us to gently peek into that process. It is also a testament to how strange the universe can be without ever breaking its own rules. Within its own domain, the world of light and electrons, QED reigns supreme. It is quite simply the most accurately tested theory in the entire history of science. Even Feynman, who was famously skeptical of too much admiration, admitted that QED was an extraordinary thing. But he also gently warned us not to get too comfortable. Nature, he liked to say, always has more up her sleeve. And while QED might be the best story we have now, it may not be the final one. Still, for now, it is a masterpiece, a quiet triumph, a gentle dance written in the language of fields and photons, performed billions upon billions of times per second all around us, and always without fail on cue. And in that quiet, precise whisper lies the light from the most distant stars, the soft glow of your bedside lamp, and the gentle pulse of the screen in your hand. All of it choreographed by a theory so subtle, so perfect, that you barely even notice it is working. But it is there, in every flicker, every reflection, every gentle breath of illumination. And from this perfect quiet dance, a new kind of machine, a new kind of dream is slowly being born. If the computers we know in our everyday lives are like careful, quiet librarians, efficient and orderly, flipping through the pages of a book one at a time, then quantum computers are more like very strange and gentle poets. Poets who can read all the books in the library at once in soft, overlapping whispers, and somehow from that shimmering cloud of words find the single perfect answer they are looking for. It sounds like a kind of magic, and in some ways it feels like it. But quantum computing is a very real and very quiet dream that is slowly beginning to unfold. And it is built upon the very same bizarre and beautiful principles that lie at the heart of the quantum world. To understand what makes a quantum computer so different, we must first meet the quieter, stranger cousin of the computer bit, the qubit. In a classical computer, in the phone in your hand, or the laptop on your desk, everything boils down to bits. A bit is a simple binary unit of information. It can be either a 0 or a 1, like a light switch that is either off or on. These simple, definite bits are the building blocks of everything your computer does. But a qubit, a quantum bit, does not have to make such a firm choice. Thanks to the gentle magic of superposition, a qubit can exist in a soft, shimmering blend of both states at the same time. Imagine a spinning coin that is neither heads nor tails until the moment you gently stop it and observe the result. While it is spinning, it holds within it the potential for both outcomes. In the same way, a single qubit can hold the states of both 0 and 1 simultaneously. And as you add more qubits, the power of this superposition grows exponentially. 2 qubits can hold 4 possible combinations at once. 3 qubits can hold 8, 20 qubits can hold over 1,000,000. With enough qubits, a quantum computer could in theory explore an astronomical number of possibilities, all in parallel. That is the quiet central idea behind quantum computing, a gentle computational parallelism. While a classical computer must test each possible path one by one, a quantum computer can explore many paths at once, not in a way that gives you all the answers instantly. The quiet trick lies in gently manipulating the system so that when you finally make a measurement, the right answer is the one that is most likely to appear. It is less like brute force guessing and more like softly shaping a landscape of probabilities so that the correct solution gently rises to the top like a single clear peak in a misty valley. But there is another quantum trick at work here as well: entanglement. When qubits become entangled, the state of one becomes instantly and intimately linked to the state of another, even if they are far apart. This allows for complex and subtle correlations between the qubits that classical bits simply cannot replicate. It is like a silent, choreographed dance between particles. If one twirls, the other twirls too, no matter how much empty space lies between them. This entanglement allows a quantum computer to perform operations that are woven together in a way that is far more complex than a simple linear sequence of steps. For certain specific kinds of problems, like simulating the intricate dance of molecules or finding the prime factors of very large numbers, this quantum approach promises an enormous and gentle speed-up. But now comes the part where we slow down and breathe a little. Quantum computers are not going to replace your laptop anytime soon. They are highly specialized tools, not general-purpose machines. For everyday tasks like browsing the quiet corners of the internet or writing a gentle email, your classical computer will remain the quiet and reliable champion. In fact, building and running a quantum computer is an incredibly delicate and difficult task. Qubits are fragile. They are like the softest of whispers, easily drowned out by the noise of the world. They can be disrupted by the tiniest of vibrations, the smallest fluctuations in temperature, even a stray magnetic field from a nearby wire. To maintain a qubit's coherence, its quiet ability to remain in a state of superposition and entanglement requires extreme and gentle care. Many of these quantum machines must be cooled to temperatures near absolute zero. That is colder than the deepest, most silent regions of outer space. And then there is the challenge of errors. In a classical computer, if a bit accidentally flips from a 0 to a 1, it is fairly easy to detect and to fix. In a quantum system, it is much, much trickier. You cannot simply look at a qubit to check its state without collapsing its delicate superposition. And you cannot simply make a copy of it to have a backup thanks to a deep and quiet rule of the quantum world known as the no-cloning theorem. So researchers have had to invent wonderfully clever and complex schemes, using many physical qubits to gently protect the information held in a single logical qubit. It is like wrapping your whispering poet in layers and layers of soft soundproof insulation so they can keep reciting their poem without being disturbed by the outside world. Despite these quiet and immense challenges, the progress has been breathtaking. Researchers have now built quantum machines with tens and even hundreds of qubits. Some have demonstrated what is called quantum supremacy, performing a highly specific and rather abstract calculation that would take even the most powerful classical supercomputer an impossibly long time. And there are real-world applications that are slowly and gently being explored. One of the most promising is in the field of quantum chemistry. Simulating the exact quantum behavior of molecules is an incredibly difficult task for classical computers. But a quantum computer is naturally suited for it. This could one day revolutionize the way we design new medicines, create new materials, or even invent more efficient batteries. Another exciting area is optimization. The quiet and difficult art of solving problems with many competing variables. Like finding the most efficient routes for a fleet of delivery trucks or allocating scarce resources in the best possible way. Quantum algorithms may be able to explore the vast landscape of possibilities and find better solutions faster. And then there is the world of cryptography, the quiet and secret art of codes. Certain quantum algorithms could one day be able to break many of the encryption methods we rely on to keep our information safe. And this has sparked a new and urgent field of research to design new kinds of encryption that even a quantum computer cannot crack. Still, we are in the earliest, quietest days of this new dream. The dream of a large-scale, fault-tolerant quantum computer is still many years, if not decades away. But what is so wondrous is how this new science takes the very strangest, most philosophical parts of the quantum world and turns them into gentle, practical tools. Superposition once a quiet, abstract puzzle becomes a resource. Entanglement, once spooky and strange, becomes useful. Even the mysterious collapse of the wave function becomes a necessary and final step in the calculation. It is almost poetic. The very weirdness that once made quantum theory so unsettling is now being gently harnessed to solve problems that were once thought to be impossible. It is like learning to tame a wild and unpredictable wind, not by fighting against it, but by learning how to sail with it. We may not know exactly where this quiet quantum path will lead, but the journey itself, intricate and full of a soft and shimmering potential, is already rewriting our understanding of what machines and minds can do. And as we learn to build these strange new machines, we are also discovering that nature itself may have been using these quantum tricks all along. In the quiet, shimmering world of quantum physics, we have come to expect things to be strange. We have met particles that can teleport through solid walls, that can spin in two directions at once, and that can form ghostly entangled pairs that whisper to each other across the cosmos. But there is a place where we usually do not expect to find this delicate quantum behavior, and that place is biology. Biology. The world of living things is messy. It is warm and it is wet. It operates in a noisy, chaotic world, full of jiggling molecules, random collisions, and a constant gentle hum of thermal energy. Quantum effects, on the other hand, are notoriously fragile. They are like the most delicate of soap bubbles, easily popped by the slightest touch of heat or chaos. That is why we build our quantum computers in freezing, silent labs and isolate our particles in a near-perfect vacuum. And yet, somehow, it seems that life itself has learned how to use these quiet quantum tricks. Take for a moment the small and humble robin, a simple bird with a surprising and wondrous sense of direction. Robins are migratory birds flying thousands of miles across continents with an uncanny and quiet precision. But what is guiding them? How do they know with such certainty which way is north? For a long time, scientists suspected that birds must have some kind of built-in biological compass. but the details of how it could possibly work remained a soft and gentle mystery. Then, a radical and beautiful idea began to take flight. What if quantum entanglement was involved? The story, the hypothesis, goes something like this. Inside the eye of a bird, there may be a special kind of protein. And within this protein, there is a pair of electrons that can become quantumly linked or entangled. When a particle of light from the sun strikes this molecule, it gently excites these electrons, causing their spins to become correlated in a delicate quantum dance. These entangled spins then interact with the Earth's own magnetic field. And this interaction gently influences a chemical reaction in a way that depends on the direction the bird is facing. In a sense, the bird may be able to see the Earth's magnetic field as a soft, shifting pattern of light and shadow laid over its normal vision, a living quantum compass. If that sounds like science fiction, you are not alone. The idea was met with a great deal of gentle skepticism. Entanglement is so fragile. Could it really survive inside a warm, bustling living cell? Surprisingly, the quiet evidence is beginning to suggest that it might. There is a growing collection of clues that points to birds and other animals really relying on a quantum process to navigate. It is not yet a proven fact, but the signs are promising. If it is true, it means that nature has figured out how to protect and use delicate quantum information in a warm, wet, biological world. A feat that our own best engineers are still struggling to perfect. Now let us shift our gaze from the sky to something green and leafy. Plants, like birds, may also be quiet masters of a subtle quantum game. Consider the gentle miracle of photosynthesis, the process by which a plant turns pure sunlight into chemical energy. On the surface, it sounds simple enough. A particle of light hits a chlorophyll molecule, which absorbs the energy, and then that energy needs to be transferred to a special reaction center where it can be safely stored. But how does that little packet of energy get from the point of impact to the reaction center so incredibly efficiently? You might imagine that it hops randomly from one molecule to the next, wandering around until it happens to stumble upon the right spot. But that would be a slow and clumsy method. And measurements of the process suggest that something far more elegant and far more quantum is happening. The energy does not seem to hop. It seems to explore multiple paths all at the same time, as though the system is using a kind of quantum coherence to find the most efficient route in an instant. Imagine dropping a single tiny marble onto a complex branching maze. Instead of rolling down one single corridor, imagine if that marble could spread out like a soft wave of water, feeling out every possible path at once, and then, in a moment, contracting back into a single point at the shortest, most direct exit. That is how some researchers believe the energy transfer in photosynthesis behaves. The energy does not wander aimlessly. It takes the best, most efficient route thanks to a quiet and fleeting bit of quantum navigation. This is astonishing, because these systems are warm, biological, and full of noise. And yet, this quantum coherence, this wave-like exploration of possibilities, seems to persist for just long enough, a few trillionths of a second, to make a real difference. If plants are quiet quantum strategists, it raises a soft and tantalizing possibility. Has evolution itself learned how to harness the strange and beautiful rules of quantum mechanics? There is no reason to think that biology would not make use of the same principles we find in our quiet physics labs. After all, nature has had billions of years to gently experiment. And any organism that happened to find a clever quantum shortcut, whether for finding its way for capturing energy more efficiently, or for sensing the world, may have enjoyed a small but crucial advantage in the quiet and constant struggle for survival. And speaking of sensing, there is one more quiet biological mystery that might have a quantum answer: our own gentle sense of smell. We usually imagine that our sense of smell works by shape. A molecule carrying a particular scent floats into your nose, and it fits into a receptor there, like a tiny key fitting into a lock. And when the key turns, a signal is sent to your brain. But that simple mechanical story has some quiet holes in it. Some molecules with very similar shapes can smell wildly different, and some molecules with very different shapes can smell almost exactly the same. One alternative and very quantum idea is the vibrational theory of smell. It suggests that our noses do not just detect a molecule's shape, they also detect how that molecule vibrates. The proposal is that when a scent molecule binds to a receptor in your nose, electrons in that receptor might be able to tunnel through the molecule. And the likelihood of this quantum tunneling happening depends on the molecule's own unique vibrational frequency. If it is true, it would mean that a part of your sense of smell involves the same quantum trick that allows particles to pass through barriers in the heart of a star. Again, the idea is still debated, but it is a beautiful and gentle reminder that the strange rules of the quantum world do not stop at the door of the physics lab. They may reach into the feathers of a bird, the sun-drenched leaves of a tree, and even the soft and gentle breath you are drawing through your nose right now. It is a humbling thought that the same strange mathematics that describes the shimmering dance of an electron in a vacuum may also underpin the quiet song of a robin and the soft green shimmer of sunlight on a leaf. Life, it seems, has always been playing with the strangest, most beautiful tools in the entire universe. It just never bothered to tell us. And as we begin to see these quantum whispers in the living world, it also helps us understand why we do not see them in the solid, everyday world all around us. At the quantum level, the world is a shimmering, gentle dream. Particles blur into soft clouds of superposition. They interfere with their own ghostly potentials, and they occupy a multitude of possibilities all at once. It is a playground of probability, not of certainty. And yet, when you look around the quiet room you are in, you do not see a world made of shimmering maybes. You see a solid, definite world. A coffee mug, a desk, a book. You interact with a world that feels consistent and wonderfully, peacefully predictable. Why is that? Why do you not see tables that are both here and also over there? Why do entire sandwiches not exist in a soft, probabilistic wave, only collapsing into a single edible reality when you open the fridge? The answer: the bridge between the strange quantum dream and our solid waking world lies in a quiet but immensely powerful process. A process called decoherence. It is the gentle and constant mechanism that explains how the quantum world gradually and gracefully loses its quantumness and becomes the classical world we know and love. Let us begin this thought with a gentle mental stretch. Imagine a single lonely electron floating in the perfect silent vacuum of deep space. It is completely and utterly isolated from everything else in the universe. In this perfect quiet, it can remain in a beautiful, delicate state of superposition forever. It can be a shimmering, soft wave of possibility spread out across space for as long as nothing disturbs it. But back here on Earth, things are not so quiet. There is air, there is warmth, there are countless photons of light drifting down from the sun and bouncing off every surface. There are molecules of gas jiggling and bouncing around. There are vibrations in the floor and tiny fluctuating electromagnetic fields. The moment our quantum object, our perfect isolated electron, interacts with any of this gentle environmental noise, it begins to lose its quantum coherence. The neat mathematical purity of its wave-like nature begins to blur. This is decoherence. It is not that the superposition suddenly vanishes. It is still there in a sense. But the quantum system, our little electron, becomes entangled with its environment. All those countless air molecules and photons that it has touched now become a part of its quantum story. And when that happens, when its quiet, private dream becomes a shared one with the noisy, chaotic world around it, the system stops behaving like an isolated, shimmering wave of probabilities and starts behaving like something ordinary, predictable, and measurable. You can think of it like this. A quantum system is like a perfectly tuned and very quiet musical note. As long as it is alone, it can hold its pure tone, its coherence indefinitely. But the moment it is played in a noisy room, its sound becomes entangled with all the other sounds, the echoes, the chatter. The pure note is still there, but it is lost in the noise. Its special coherent quality has dissolved into the environment. Decoherence is a gentle and constant erosion of quantumness. It does not require a conscious observer or a big dramatic measurement with a piece of lab equipment. It just needs time and contact with the outside world. And it happens incredibly, unimaginably fast. For a tiny microscopic object like a single electron or an atom, we can isolate it well enough in a cold, quiet vacuum that its quantum behavior can stick around for a while. But for a macroscopic object, something you can touch and see like a grain of sand or a cup of tea, decoherence happens almost instantly. The more massive and the more complex a system is, the faster its quantum weirdness dissolves into classical certainty. The time it takes for a dusty speck of pollen floating in the air to lose its quantum coherence is a trillionth of a second. So fast that for all practical purposes, it is never in a quantum state at all. That is why you do not walk into a room and find your shoes in a quantum blur. Their constant, gentle interaction with the air, the light and the warmth of the room has already pinned them down to a single definite state. In this way, decoherence does not destroy quantum superpositions. It simply hides them. The possibilities are still there in the principle, but they are now entangled with so many countless and untrackable particles in the environment that we can never access them or see their ghostly interference. They become, for all practical purposes, classical, even though deep down at the quietest level, everything remains quantum. This also helps us to gently understand one of the oldest mysteries in quantum mechanics. How do we get from a world of soft probabilities to a world of definite outcomes? Decoherence does not solve this puzzle completely. It does not choose which single outcome will occur, but it does explain why we only ever see one outcome. It explains why Schrödinger's cat, if it were a real experiment, would never truly be in a shimmering state of both alive and not alive. The constant interactions with its own warm, complex body and the air in the box would have already forced it to look like one or the other. Decoherence creates the illusion of a collapse by gently bleeding the quantum information, the coherence, out into the wider world. The result is a kind of statistical and gentle consensus. The wave function is still there, but it no longer behaves in a way that we can see as a coherent, shimmering wave. And this gives us a soft and gentle bridge. A bridge between the strange, misty world of the quantum and the solid, reliable world of the classical. It shows us that the world we see is not a separate thing from the quantum realm. It is shaped by it. It is filtered through a continuous and gentle interaction with everything that surrounds it. So the next time you pick up a book or open a door, you can thank decoherence for the fact that it behaves in the solid, predictable way that you expect, for taking a universe of shimmering maybes and presenting it to your senses as a firm and gentle handshake. It is a quiet and constant phenomenon. No sparks, no flashes, just the slow, graceful, and inevitable loss of possibility, leaving behind the stable, beautiful patterns that we call reality. And in this gentle transition from the quantum to the classical, even time itself begins to play by strange and subtle rules. Imagine setting up an experiment, so strange, so impossibly delicate, that the very act of deciding when to look seems to reach back in time and gently affect what has already happened. It sounds like a story from a dream, or perhaps a gentle philosophical confusion. But this is precisely what happens in a series of quiet and profound experiments that toy with the very foundations of our understanding of cause and effect. They go by gentle, wondrous names, like the delayed choice experiment and the quantum eraser. And if you were hoping that the quantum world would finally start to make simple, logical sense, well, this is the point in the dream where even time itself begins to softly shrug its shoulders. Let us begin with a familiar and gentle setup: the double-slit experiment. We send a single particle of light, a single photon, toward a wall with two tiny slits in it. Behind the wall, a screen waits to record where the photon lands. If we do not observe which of the two slits the photon passes through, it behaves like a ghostly wave. It seems to pass through both slits at once, and it creates an interference pattern on the screen, a signature of its wave-like, uncertain nature. But if we place a detector at the slits to find out which path it took, the interference pattern vanishes. The photon behaves like a simple, solid little bullet, choosing one path and one path only. The simple act of knowing the path kills the ghostly wave. So far, so strange. Now, let us get mischievous. In the delayed choice experiment, first dreamed up by the physicist John Archibald Wheeler, you set up your experiment in the same way. But you reserve the right to decide whether you will measure the photon's path or not after the photon has already passed through the slits. In other words, you delay your choice. Will you act as a quiet detective and observe which path it took? Or will you let the photon remain a mystery, a shimmering, wave-like possibility? Here is where the dream becomes surreal. The pattern that forms on the screen will perfectly match whatever choice you make, even if that choice is made after the photon has supposedly finished its journey through the slits. It is as though the particle in its quiet and lonely journey somehow knows what your future choice will be, and it adjusts its past behavior accordingly. It either behaves like a wave creating an interference pattern, or it behaves like a particle creating two simple spots, all depending on a decision that has not even been made yet. It is enough to make a clock softly melt. The delayed choice experiment suggests that the quantum world does not commit to a single definite reality until it is absolutely forced to. And that forcing can happen not just in space, but across time. The act of observation does not just determine the outcome. In a soft and gentle way, it might also determine the history. And then the quantum physicists said, let us make this even weirder. Enter the quantum eraser. In this beautiful and intricate twist on the experiment, you first mark the photons in a way that allows you to know which path they took. As expected, this act of marking them destroys the interference pattern. But then, using a clever quantum trick, you can choose to erase that which path information long after the photons have already been detected on the screen. And when you do that, when you gently erase the knowledge of their past, the interference pattern comes back. The particles behave like waves again retroactively, as though they had never given up the ghost of their uncertainty in the first place. This raises a deeply unsettling and wondrously soft idea. Reality might not be finalized until all the possible information about it is settled. Not just at the moment of the event itself, but also at the moment we decide what to do with the memory of that event. So what is going on here? One gentle and tempting way to dream about this is that information, not solid physical matter, is the true and fundamental currency of the universe. In the quiet quantum world, outcomes are not locked into place until you ask a question that has a definite answer. Until that final moment, all possibilities remain gently entangled in a hazy, shimmering soup of maybe. This does not mean that we can change the past or that time travel in the way we imagine it in stories is real. Rather, it suggests that our usual simple picture of time as a straight one-way street might not apply at the quantum level. Events in the quantum realm are not always chained together in a neat, tidy line of cause and effect. They are part of a strange and holistic web where the final pattern only emerges when the entire system from beginning to end is considered. Some physicists describe it in terms of entanglement and correlation, not of causation. The particle does not know what you will do in the future. It is just that all the quiet pieces of the experiment, the photon, the slits, the detectors, and your final choice are all part of one single inseparable quantum story. And your choice at the end simply defines what kind of patterns are visible in the final telling. Others lean into a strange and beautiful idea called the block universe. A dream where all moments in time, past, present, and future, exist simultaneously, like the individual frames of a long and silent film reel. In this view, your choice does not travel backwards in time. It was always there, a part of the grand, timeless quantum story. And still others will gently shrug and say, "Shut up and calculate." The important thing, the quiet and wondrous takeaway, is this. The universe is under no obligation to conform to our common sense ideas of time or cause or reality. Our classical intuitions are built for the large, slow, and gentle world of macroscopic objects. But down in the quantum mist, the rules are softer, less linear, less local, and much, much stranger. These experiments do not break the laws of physics. They simply reveal the breathtaking and gentle richness that lies beneath them. They show that the quantum world is not just a smaller, tinier version of our everyday world. It is something fundamentally different, playing by a quiet and mysterious logic all its own. So if time ever feels like it is playing gentle tricks on you, just remember, on the quantum level, it probably is. And this gentle trickery, this softness in the rules of cause and effect, leads us to the final quiet question of the dream. Is the universe at its heart a story that is already written, or one that is being made up moment by moment? If you were to zoom in far enough into the very heart of the universe, past the swirling galaxies, past the quiet molecules, past the atoms themselves, you would eventually arrive at a world where certainty slips softly through your fingers. A world where outcomes are not determined, but are described only in the gentle language of probabilities, where particles do not have a definite position until you look. And even then, the position you find is merely the result of a quiet cosmic dice roll. Welcome to the quantum universe, a place that is not just small, it is at its very core uncertain. Quantum physics suggests that randomness may not just be a part of our world, but that it may actually be the foundation upon which everything else is built. This idea does not sit comfortably with everyone. In fact, it was this very thought that made Albert Einstein so famously uneasy. He once declared in a quiet moment of philosophical protest, "God does not play dice with the universe." A beautiful line that has been whispered for nearly a century in every quiet conversation about physics and fate. But let us gently unpack what this randomness actually means and what it does not. In the old classical world, the world of clockwork and certainty, everything behaves like a perfectly oiled machine. If you know the exact position and the exact speed of every single particle in a system, you can in principle predict its entire future with absolute unwavering precision. It is a neat deterministic framework, like lining up a long row of dominoes and knowing exactly how each and every one will fall. Quantum mechanics gently breaks that chain. It replaces those precise, definite predictions with the shimmering, soft cloud of the wave function, a mathematical object that describes all the possible outcomes of a particle's behavior. And when you make a measurement, the wave function collapses into just one of those possible outcomes. But which one you will get is not determined ahead of time. It is, as far as we can tell, genuinely and fundamentally random. That is not a code word for "we just do not know enough yet." It is not the result of human error or of missing hidden information. It seems to be baked into the very structure of reality itself. The best we can ever do is to calculate the probability of each possible result and then gently and quietly accept what shows up. Now, some ways of dreaming about the quantum world, like the many worlds view, try to dodge this randomness. They suggest that every possible outcome does happen just in its own separate branching universe. So when you measure a particle and it spins up, there is another silent version of you in another universe where it spins down. In that story, there is no randomness, just an infinite number of definite outcomes. But even if that beautiful story is true, you, in your own quiet branch, can never predict which version of the story you will find yourself in. From your point of view, the experience is just as unpredictable. This raises some of the deepest and softest questions we can ask. If a true fundamental randomness exists at the very foundation of reality, what does that mean for cause and effect? For the quiet and gentle unfolding of our own lives? For the laws of nature themselves? It might feel unsettling at first, the the idea that the universe is not operating on some grand pre-written script, but is in a sense improvising as it goes along, that there is a fundamental looseness, a softness in the very weave of reality. And yet this quantum randomness is not the same thing as chaos. In fact, the laws of quantum mechanics are astonishingly, breathtakingly precise in their predictions. The theory does not say that anything could happen. It says here is a very specific and limited list of what can happen, and here are the exact odds of each. When physicists test the predictions of quantum theory, they find an agreement with their experiments that is almost miraculous. So even if the individual quantum outcomes are random, the structure of that randomness is deeply and beautifully orderly. It is a little like rolling 1,000,000 dice and finding that their average sum is always predictable, even though the result of each individual die is not. The behavior of large numbers of particles becomes so reliable, so statistically certain, that it gives rise to the solid, predictable laws of classical physics that we experience in our everyday world. This is why your coffee mug does not suddenly tunnel through the table, even though each of its individual particles has a tiny, non-zero chance of doing so. In this sense, randomness is not a bug in the system. It is a feature. It adds a gentle, creative flexibility to the universe. It allows for novelty. It might even be essential for the very existence of life and consciousness. Think of the quiet and random mutations that drive the slow and gentle unfolding of evolution. If every single biological event was strictly determined, there would be no variation, no branching paths. But throw in a little quantum randomness, a change in a gene here, a soft transmutation there, and suddenly the universe has options. In the quantum realm, randomness is the quiet engine of variety. It gives rise to a breathtaking complexity from the simplest of beginnings. And it does so without ever breaking its own rules. Because the rules of the quantum world are statistical, not prescriptive. Some find a deep and gentle comfort in this unpredictability. After all, a purely deterministic universe can feel like a cold clockwork prison where every thought, every action, every gentle feeling is just the inevitable echo of particles obeying rigid ancient laws. But a probabilistic universe? That is a universe where the unexpected can happen, where the story is not yet written, where outcomes are not set in stone but are drawn softly from a deck of possibilities. Of course, this randomness also comes with a deep and quiet mystery. When we observe a particle and it chooses one state rather than another, why that one quantum mechanics does not offer a reason. It just gives you the odds. It is like flipping a coin and getting heads. There is no deeper hidden explanation for that single outcome. Just that it had a 50% chance of happening. And this has a gentle philosophical weight. It suggests that the universe may not be fully knowable in the old classical sense. That there is a soft and gentle ceiling to our certainty. A quiet boundary beyond which our questions do not have definite answers, only a range of beautiful, shimmering possibilities. So perhaps the universe does play dice, not recklessly, but with a quiet and subtle elegance so refined that it creates galaxies and atoms and thoughts and time itself. And while we may never fully tame that gentle randomness, we can come to appreciate it, not as a flaw in the cosmic machinery, but as the soft and constant hum of possibility woven into the very fabric of everything. And in that quiet hum, we find not just a story about physics, but a gentle reflection of our own human place in the cosmos. If quantum physics were merely a set of strange and elegant equations, it might still be considered one of humanity's greatest and quietest intellectual achievements. But what makes it truly special, truly profound, is that it does not just describe the dance of particles and the shimmer of probabilities. It gently invites us to reflect on something deeper, what it means to know and what it means to be. Because in peeling back the soft layers of the universe, quantum physics does not simply reveal new answers, it reshapes the very questions themselves. We tend to think of reality as something solid, fixed, out there, something that exists in its full and definite form, whether we are here to look at it or not. But the quantum world gently and persistently disagrees. It suggests that on the smallest of scales, reality is not fixed at all. It is a soft and shimmering set of possibilities, like a half-remembered dream, waiting for an observer to gently nudge it into a definite form. When a particle exists in a state of superposition, it is not just undecided. It is, in a very real sense, all of its possible states at once. A soft smudge of probability, not a single hard dot. And when we measure it, when we gently ask it to reveal itself, it settles on one single outcome, as though the universe had softly exhaled and chosen a story. This raises a quiet and unsettling thought. If the act of observation plays such a crucial and creative role in shaping what is real, are we as observers as separate from the universe as we once believed? Or are we, and our quiet, gentle questions, a part of the grand entangled dance? For a physicist, these are technical questions to be explored with mathematics and experiment. For the rest of us, they feel almost spiritual. But quantum physics is not here to offer easy answers. It is not a shortcut to a grand mystical truth or a factory for gentle metaphors to use in self-help books. And yet, it does leave us with something precious, a deep and quiet humility. It reminds us that our everyday intuitions, our common sense ideas about space and time and matter and cause are not the final word on how the universe works. That the familiar solid world we navigate each day is just one version of reality. A version filtered through the gentle lens of our evolution, shaped by the limits of our senses, and stitched together by the quiet comfort of habit. In this way, quantum mechanics becomes more than just physics. It becomes a soft and gentle mirror. A mirror that shows us the quiet edges of our own knowledge, the soft boundaries of our understanding, and the breathtaking and beautiful strangeness of the universe we are privileged to call home. Think of Schrödinger's cat, not as a literal and unfortunate feline trapped in a cold logical paradox, but as a gentle metaphor for the way we all live so often in a state of quiet and gentle uncertainty. For how we constantly juggle conflicting possibilities, half-known truths and almost certainties. Whether it is waiting for the result of a medical test, or for a letter to arrive, or simply wondering if it will rain tomorrow, we exist quite often in a quantum state of our own, a superposition of hope and fear, of expectation and doubt, a soft and shimmering layer of possibilities held gently over each other until time or choice or the gentle hand of fate collapses the wave. And maybe that is the secret, quiet beauty of quantum mechanics. It is not telling us that the world is unknowable or meaningless. It is just telling us that the universe is under no obligation to be obvious. there is a softness to that realization, a quiet and gentle freedom. If certainty is not guaranteed, then neither is limitation. If the world is not pinned down until it is observed, then possibility is always and forever alive, flickering softly just out of our view. Even the word quantum itself has a kind of gentle poetry to it. It comes from a Latin word quantus. How much? How much light? How much energy? How much is this gentle, shimmering particle allowed to be or to do? But more than that, it is a word that points toward boundaries, toward discrete, indivisible packets, the smallest, softest allowed unit of change. And maybe there is something meaningful in that too, that even in the vast and swirling and seemingly infinite confusion of the cosmos, there are limits, there are minimum steps, quiet, gentle thresholds that must be crossed. Not everything is continuous. Some things change in soft and sudden leaps. When you dream, you do not do it one atom at a time. You leap into worlds that do not exist until suddenly they do. You witness impossible things until they feel natural. And when you wake, you may not remember all the rules of that strange world, but you carry back with you the gentle and lingering feeling of its possibility. Quantum physics feels a little like that, like waking from a strange and beautiful dream and realizing with a quiet sense of wonder that the world is weirder and wilder and more wonderful than you had ever guessed. Of course, this can be a little unsettling. We like cause and effect. We like knowing. Certainty has its soft comforts. But maybe certainty is also a little overrated. Maybe it is okay to live with questions that do not yet have answers. To wander in a quiet and misty forest of probabilities without demanding to know which tree is the real one. Maybe that is where wonder lives, in the soft and gentle spaces between what we can grasp and what we can only and ever glimpse. The great physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant it as both a gentle joke and a profound truth. Even those who work with the mathematics every single day, who build beautiful and complex machines and models from its quiet predictions, will admit that quantum physics is not something you get in the usual way. It is something you accept, like a poem or a dream. It works, it is precise, it is testable, and yet it refuses to be pinned down by our ordinary everyday logic. And maybe, just maybe, that makes it more honest. Because the universe was never ever obliged to be simple. It just had to be. So as we drift now through the quiet, shimmering ripples of quantum thought, maybe the most important lesson is not about particles or probabilities, but about perspective. To see uncertainty not as a flaw, but as a feature. To let go gently of the need to know everything. And to rest in the strange and beautiful truth that we are a part of a cosmos that is still and forever unfolding, still choosing, still shimmering with a soft and endless possibility. A place where even the emptiest vacuum is not truly empty, where time can gently flex, where light can forget how to behave, and where in the end reality dreams too. And so, the night drifts onward. Thank you for listening. Whether you were still wide awake, gently drifting, or already halfway through a dream of your own, we have wandered a long and quiet way tonight. Through soft, imaginary slits in cardboard, and through gentle thought experiments with cats. Through shimmering, rippling fields, and into the strange and mysterious erases of time. We have met particles that behave like waves, and waves that act like particles, and forces that play by quiet and subtle rules, written in a language we are only just beginning to learn how to translate. And somewhere along that gentle, winding journey, we began to see not just the oddness of the quantum world, but its quiet and profound beauty. At first glance, it might all seem too strange to be real. A universe where something is not truly anything until it is observed, where the neat, straight line of cause and effect gets blurry and soft around the edges, where a single tiny particle can be here and also somewhere else. But what quantum physics gently reminds us over and over again is that the world we know, the solid and predictable world that we can touch and taste and measure, is only the surface. Beneath it lies a softer world, a stranger world, yes, but also a world that is more flexible, more open to surprise, a world built not on the hard, cold stone of certainty, but on the shimmering, gentle mist of possibility. And we are a part of that world, not separate from it, not merely observers peeking in from the outside. We are made from these very same strange quantum fields. The atoms in your fingertips, the gentle light that is reflecting from your eyes, the quiet oxygen in your lungs. All of it, every single part obeys the same soft, uncertain laws. You are not just in the universe. You are of it. And does that not feel just a little bit poetic? Back at the very start of our journey, I asked where in the world you might be listening from tonight. Maybe you are curled up in bed under the soft and gentle weight of a heavy blanket. Maybe you are gazing up at the ceiling, your own thoughts flickering like quiet, distant stars. Maybe you are far from home or just far from sleep. Wherever you are, I hope you have found something in this quiet journey, something soft or strange or simply still. And remember that when we stare into the very heart of matter and we ask the deepest, quietest question, what is real? Quantum physics does not offer us a final, simple answer. It offers us a mirror, a shimmering and shifting one. A gentle reminder that knowing something deeply does not always mean understanding it completely. That our questions can be just as beautiful as our answers. That mystery is not a failure of our knowledge, but a gentle and wondrous feature of the universe itself. It can be tempting to wish for more clarity, to want the universe to lay out all of its rules plainly and simply, and to play fair. But maybe in this tangled and gentle uncertainty, there is a different kind of comfort to be found. A quiet truth that whispers, you do not need all the answers to feel at home here. Because even if the particles are uncertain, the moment you are in is real. The breath you just took, the thought that just drifted by, the weight of your body gently sinking into stillness. That too is a truth that is enough. Good night.